I'm Dr. Bly, and if your name was on that list, then you're in the right place. Let's start with, I guess we'll start with syllabus. This semester, we've got a new format. So if you're taking any other courses, you've probably seen this before. It's standardized into 3 parts. The first part and the third part are chiseled in stone. There's nothing I can do about that. But the part 2 in the middle is where, actually where you want to concentrate focus your eyeballs on this. Part 2. And it starts on page 6. Let's see, anything? Oh, page 1. The textbooks are there. I think since I'm only going to use one exercise from the custom lab manual. So if you won't tell anybody, don't buy it. The only reason I have students buy those things is because I extract some of the information from those and modify them and just redistribute them. And I just don't want to violate copyright, but I'm only going to do one out of that lab manual for this class. And the rest of them I'm going to bring myself. They're well, I can't say they're all my creation, but they've been heavily customized. So you only need the textbook, the chemistry, the central science, Brown, LeMay, and Bernstein. So we can skip all the rest of that stuff. That's peculiar to the college. And go on to, yeah, it's recording. And go on to the page 6. So you got my name, there's my telephone numbers. I've got 2 of them that you can use. One of them is my office for New River, where I'm a full-time employee. This is my adjunct side job. But if you call that number and I'm there, of course, I'll answer it. But if I'm not, just leave a message. If you're not in a big hurry, it converts those messages into a voice file, or what do you call it? WMVs, I think. And it attaches them to an email and sends them to me. All my emails come through my phone, so I'll get it pretty quick. But if you want a quicker response, you can text me on my cell phone. That's the best way. The first time you text me on my cell phone, use your name and the course you're in. And then thereafter, you can text anytime, and it's all in a thread, right? So your thread will be over here, and I can just look at the top and say, oh, that's who that is. So just identify yourself the first time you do it. My office hours there. I also got you a copy of my schedule. And there's probably a schedule in the syllabus. I think I put one in here too. Yeah. Okay. So that's where I am supposed to be at any time of the day. And you can see where my office hours are. Those office hours are for the benefit of administration. They force us to schedule 10 office hours. But my policy is my students can meet with me anytime they want. As long as I'm not in a class, we can meet. We can either meet face-to-face. If you're ever in the Beckley area, you can come out of college. My office is 129 on the Raleigh campus behind the Irma Bird Center. Or, probably more convenient, is we can Zoom. If you contact me and tell me you want to meet at a certain time and I'm not doing something else, then I'll open up my personal Zoom account and you can Zoom into that. And that information is contained where? There it is. Right above the office hours. That meeting ID, 295-716-1648. That's my personal Zoom account number, and that's where I'll be if we need a personal meeting. So all you need is a computer with a camera and a microphone. Let's see. Before I do schedule talk, see if there's anything else. Okay, we'll look at the schedule. The schedule looks complicated, but there's a method to it. So let me explain. Of course, down the left-hand side are the day dates. Those are obvious. And then the lecture activities have a heading here and a lab activities over on the right. And they correlate with one another. The lecture activities under reviews and exam, it just tells you when we're going to have exams, when we're going to have reviews down that column. So you can follow that down, and that tells you when to be prepared for that exam. And we always have a review session the week before the exam. So during that review session, you bring your problems in. If you can wait that long, if you can't, then we can tutor personally. But if you bring them into the review session and we solve them here on board, it might help somebody else in the class. Now the column under PowerPoint lecture chapters, I teach a course so similar to this one at New River. I use the same PowerPoint sets that I do over there. So I have to modify a new set. That's why they won't look anything like your textbook. But what I've done is right next to that, corresponding chapters in brown, that's where you'll find the information that's on that slide set. So I've correlated my source of PowerPoint slides with your textbook. And most of them, they go along pretty well. Like we're going to do chapters 1 and chapter 2 in my book. And fortunately, that correlates with your chapter 1 and 2. Let me see if I can find one that doesn't quite match up. Okay, when we get to gases, on the next page, chapter 5, gases for me, but it's your chapter 10. Let's see, and thermochemistry is a different chapter. My chapter 7 is split into 2 chapters in your book. So go figure. And then when necessary, like my chapter 8, chapter 9 are covered by your chapter 8 and part of 9, and then my 9 is the rest of your 9. Okay. If it gets confusing, just ask me and I'll try to explain. And then of course the labs are scheduled not every week, right? Usually what I do is schedule labs on a review day because reviews generally take less time and that gives us more time in the lab. And the lecture days usually take more time than is allowed during the lecture slot. So I have to go over. So we won't have lab on that day. We'll just stay in here. Let's see. Oh, so you might wonder, right, we go in and do a lab and you have to do a report on it. When is that report due? So I've got it in here in red letters over on the far right side. Lab number 2 is due. So which one is lab number 2? Well, you go back here and look under that order column. Okay, the order column says 2. So this is the lab we did on that day, and this is when it's due. Okay. Actually, my rule is the due date for a lab that we do, say this week, the due date is the next time we go into the lab for the next exercise. So if there's a week gap, if there's a 2-week gap, it's all the same to me. It's not due till we go in for the next lab. And let's see. I apologize, there is a final exam. I couldn't help myself. So we're going to have 8 labs and 7 exams. So you can spread the misery out, plus the final. So I need to talk about the grading scheme, don't I? So what are they worth? Let's see. Next page, page 8. Yeah, page 8. Okay. All the chapter exams are worth 60% total. And then the final exam is worth 20%. Lab reports are worth 15% of the total grade. And then I throw in lab skills and lab notebook. Some of that is sort of qualitative, semi-qualitative, quantitative, and there's qualitative in there too. So that gives me some leeway, right? If you're borderline on one grade or the other, and look, the skills in the lab notebook look pretty good, then that helps me, helps my feelings when I want to bump you up to the next grade. Okay. We're on a 10-point scale. I think that's pretty common for most instructors. So if you're aiming for an A, just average 90 and you got it made. The rest of this stuff is, well, these things right here, these tables, that's for correlation for assessment, right? That doesn't mean, it probably won't mean anything to you. And I think it's in there to satisfy the Higher Learning Commission when we go up for reaccreditation. So let's skip down to, see if I didn't already skip something. Oh, you'll also notice in here these gray bars, those dates are not meeting times. Those dates, in fact, there shouldn't be any of them on Fridays. For instance, go down to 11th of October is on a Monday. That's when the mid-semester grades are due. So anything before that that's graded will go into that grade. Yeah. And then I've got Thanksgiving recess marked off. Here's one that I point out, but I hope you don't ever have to use it. Last day to drop with a W. And then final grades have to be reported on the 13th of December. So when we take an exam, and I'm pretty sure I can manage it because we've only got 4 or maybe 5, is as you finish your exam, just bring it to me and I'll start grading immediately. And I try to set it up so I can grade them fast. So there's lots of multiple choice. And whenever I have to, I put in short answers. And maybe you might have to write out a chemical equation, stuff like that, or maybe draw a structure. But I try to set it up so I can grade it quickly, get it done before you leave class that day. Then you know where you stand on that topic, and it helps you judge what to do next. Okay, other course materials. You need a calculator. If you don't already have a scientific calculator, just if the box says scientific on it, you're good to go. And these other functions in here, I add those simply because once you get your scientific calculator, I want you to know how to use those functions. Because we're not going to spend time on learning our calculators. There's so many different types. You wouldn't probably want to touch my calculator. It's a reverse Polish notation, which is actually, it's better than algebraic. Because algebraic, if you have complex formula, you've got to put parentheses everywhere. But with a RPN calculator, it's a breeze. It just takes a little getting used to. Anyway, you can use any type of calculator, cell phone, laptop, for anything except exams. So you might as well buy a calculator and get used to using it. Because cell phones are just way too smart for exams. I record every lecture and every review session on Zoom. So it takes me a few days to process the video, but I upload it to YouTube and then take the link and put it in Blackboard. So if you want to go back and view what we did that day and see if you missed anything, then, or if you're absent that day and you can't zoom in because if you go in Blackboard, there's a Zoom link on the left-hand side of the main page, and you can zoom into the meeting if you're physically able, if you're not deathly sick, and you're just, you can't make it for some other reason, family issues or whatever, then you can join through Zoom. But I remember taking classes as a student, and for the ones back then, you only had tape recorders. You didn't have video stuff. So I would take lectures. I was sitting in class, and then I'd go back to my domicile and review my notes along with the audio, and it's amazing what you miss. about 50%, just goes like that. Okay, so the YouTube videos are there to review. Let's see. Okay. We might as well talk about it while we're here. Lab, stuff you need for the lab. Okay, you need a bound notebook. You can bring, yeah, I brought some with me. This type. Over the years, my students have complained about finding them. It's hard to find these things, apparently, for a reasonable price. You can go online and probably get one for $4 or $5, but I don't want to pay that much. I want to go to Walmart and pay $1. And I had a student tell me the other day, oh, I went to Kroger and got one for 56 cents. Ooh, I need to go by there and buy up a bunch. But they look like this. They look just like a composition notebook, only they're quadrilined. So that's so you can, if you need to, you can draw graphs. So you can either take your chances or I'll sell you one for $1. Because that's what I paid for it. But I'll talk about setting that up a little later. This is just the part where I say you're going to need that. No spiral bounds and no loose leaves. They have to be glued and sewn together. Right. Just think of this as it's like you got a job with a new employer in a lab, and you have to keep a lab notebook that's permanently bound. And when you leave that company or that employer, it stays. They keep it. It's their property. Okay, so you're going to need a lab coat too. Right. Knee length, hopefully in better condition than this one. I've tried to get this stuff out, but some of it's permanent. Gives it character. I'm not sure where to find a brick and mortar store in the area to get lab coats. I would have thought that there'd be one close by because we got a hospital, but I don't know. If you know anybody in the hospital, you can ask them. But some of my students just order one online. Let's see. Do we have enough time to get one that way? We're going to do a lab. It doesn't require a lab coat today. 24th of September. Nope. Sorry. Looking at the wrong one. Safety, graphing. Lab techniques. 10th of September. So the 10th of September is the first lab we go in where you'll need protection. So if you can get one by the 10th of September, you'll be good. Eye protection. Now, we have goggles and over glasses in the lab, but they're so old, they've been so used so much. It's probably like looking through a fog. So you may want to invest in eye protection too. Gloves, we're generous. We give you all the gloves you need. Whether it's your size or not, I don't know. Like you've got really big hands. I like mediums. I think if you use their model and say, all right, what size do you need? They probably say I need a large, but large are too baggy. I like to put medium on it. They're really tight, gives me good tactile senses. Anyway, we talked about regular exams. Let's see. Lab exercise reports. Okay, I'm going to tell you what you need, and then we'll talk about that in detail later. But for reports, if we look at the schedule again, it identifies on the schedule whether the report is informal or formal. There's a major difference. The introducing graphing techniques. That'll be the one we do next week. Is an informal report. So what that means is you just take the lab document in the lab with you and you fill it out. It's got spaces for information. We also do that for the next one, lab techniques. So the first formal report will be due on, I guess, lab number 4, Boyle's Law. Okay, so you need to know, if you've never written a formal report, has anybody here written a formal report before? No, you're all newbies. Okay, that's fine. So I gave you samples. Let's see. Oh, it's still in the bag. This is the whole course right here. A 3-ring binder. Let me flip over to the lab section. There we go. No, that'd be easier. This thing's gonna fly apart. Come on. Leave it alone. I'll just use one of these. Let's see. Lab start. Here. Well, this is a safety document. Here we go. So this one is what your lab notebook should look like, similar to it. Yes, I just when the COVID thing was going on, we had to do lectures and labs remotely. So when my students were getting graded on their lab notebook, they had to photograph or scan, send it to me. So I just took one of them and removed their personally identifiable information and show you what it looks like. So when you go into your lab notebook, you'll identify it here. I told you I was going to do this later, didn't I? Might as well do it now. The front cover will have the name of the course, your name, the name of the course, and the semester. That's all you need there. Then you want to go in and number every page. So let's use this book to illustrate. So open it up on the first page. There you go, number 1 right here, in ink. No reds. Red's my color. And then you flip it over. See, there it is. And that's page 2. So notice all the right-hand facing pages are odd, all the left-hand facing are even. And when you fill this thing out, when you start putting information into it, always prepare it only on the odd pages. Leave the left-hand side blank. That's for overflow, for drawing graphs, whatever else. And then you number it all the way to the back. And I think there are 200 pages. But certainly as you number through, you know that the right-hand side should be odd. So if you get down here and you start to write an even number, you're keeping track in your head and you say, okay, next number is, it has to go here. You know something went wrong. Just go back and make your correction. How do you correct in a lab notebook? Draw a line through it. You never erase, you never white out. Just draw a line through it and make the correction. It doesn't have to be pretty. I know some people are I don't know if you're OCD, but just like to have pretty notebooks. If you want it to be pretty, then be prepared to make it pretty when the first time you write it. Because you're not going to write in a separate scrap of paper and then transcribe it. Everything that happens in the lab goes in here. Okay, let's see. Number the pages and table of contents. So on the first page, you'll write table of contents up here, just like in this example. Table of contents. And then you write the name of the experiment and the page it starts on. You don't have to write start to end. That's when you first put it in there, you're not going to know where it is. You just put the start page. And this will fill out as we go through the semester. And then you go over here, maybe skip a couple of pages and put the title of your thing. And then what do you put in there? Right? So you go to your hard copy, the method that's handed out. And let's see, example here. Yep. And the thing about it is, if you fill out your lab notebook with this structure, when it comes time to write a formal lab report, it's easy because the structure here is the same as it is in your report. So you have the title, you have objectives, you know, why are you doing the experiment? What are you supposed to learn? You may even put a hypothesis in here. We'll talk about hypothesis later. Then you put in, I noticed just a minute ago that this student doesn't have, it's got a section missing, safety. You make a comment on safety. Is there anything that I really need to be wary of in this lab? And then the materials that you're going to need. Then you may have some pre-lab questions that need to be completed before you come in the lab. Okay, they go in here too. Answers and all. And then notice that this page is blank, and you go to the next odd page. The date needs to go in here somewhere. Either you put the date here or you put the date in the table of contents. Either one is fine. Then you put your procedure in. The procedure, when you fill this out in your lab notebook, the procedure is do this, do this, do this. Like weigh out, blah, 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 and, dissolve it in such and such, whatever. That's the main difference between this and your report. When you write your report, you don't say what I'm going to do, you say what I did. So as you're going through the procedure in the lab, something may change, or you make an observation, right? This person had to make a correction. I'm not sure whether that correction was before or during the lab, but the correction was made. And then when you write your report, you write it in the past tense. So this is what was done. You don't use first person, you don't use second person. You don't say I or you. You use the third person always. And I've got an example of that. So it's no mystery. It's not like I tell you to do something and then you have to wait till I grade your paper to see if you got it right. I'll show you how it's done. Okay, so this person forgot to put their data in over here. So they went over to the facing page, the even page, and put a place for the data. And notice when you make a place for your data, it's a good idea to leave spaces, identifiable spaces for the numbers you're expecting to get. That's a good habit to get into, because if you are in the middle of an experiment and you're going down, you're putting in numbers and you're making observations, and you look up here and there's something missing, then you better stop and say, is that missing? Is it supposed to be missing? Was the method modified so that this should not be collected? Just exit out. Or did I miss something? So if you did miss doing something, then you probably want to stop sooner than later, because you have to go back and do it all over again. Then we have procedure, places for data. This person took the data and generated a plot of the data in Excel, and then cut and pasted it, which is fine, except they did make one mistake, and I didn't catch it before. You sign across the boundary between the pasty and the underlying page, initial or sign, so that if it's missing, you'll see part of your signature missing. And I mean, you may not be able to retrieve it, but at least you know something's not kosher. Let's see, calculations. There's a section on calculations. Now, in here, you will do all the calculations that you have to do. But if they're repetitive calculations, then when you write your report, you only need to show me one of them. If you're going to do it over and over and over again, just show me one time. Let's see, more calculations. Then there may be some post-lab questions, right? And when you're filling out your notebook the first time, you just you make a space for it. Some students like to write the question out here and then put the answer. But as long as it's numbered, identified, numbered the same way as in the hard copy, then I know where I can find it. I don't like to guess when I'm trying to grade a paper. I might guess wrong, you know, and then where would you be? Okay, so now we go over there. Oh, this person left something else out. There should be a section on summary and conclusions. Because that's one of the sections that needs to go into your report. Summarize what happened. You don't have to say infinite detail, just say in general, this is what happened, this is what we found. And think about it. This is where you have a chance to do some critical thinking about what happened in the lab. Say if you did have a hypothesis in your first statement, in your objectives, then did your experiment confirm or deny the hypothesis, for instance? Okay, I'll show you an example of a report here in a second. Let me see. Let me take this in a logical step. Let's see, what did I have next? Oh, let me grab one of these. Okay, common errors in writing a lab report. This is helpful information. If you read through this, and you can just skim through it the first time, and then go back and detail it, particularly if you're trying to write a report. And this will help you avoid common errors. So I'm not going to jump on that one too hard. It does have, let's see, something. It is missing something. It's missing calculations. I should have put that in there too. Or maybe I'm just commenting on these sections. Down at the bottom of the first page and the top of the second page, those sections. Right. So when you write your report, it will have a title page. And here's a sample. I got a sample report here. Yeah, let's look at the sample report. It's the one with this thing on it. This is the rubric that I use to grade reports. Tells you what I'm looking for. So down the left-hand side are the categories, and then across the top are the points awarded based on how well you provide information for that category. So if you go down the left-hand side and it's perfect, then 12 points times 9 is 108 points. So you can get more than 100%. So the top line is just, are all the sections there? If you're missing some sections, then you lose points for that. The next one is spelling and punctuation. That one gets me every time. When students misspell words and don't punctuate properly. Nowadays, you've got word processors that'll almost do that for you. Right? And then what you want to do is once you finish your report, you want to proofread it. So what I do is when I write something like that, when I used to write things like that a lot, I'd set it aside for several hours and then come back and look at it and say, does it still make sense? Can I follow my own logic? Or if you got someone that's maybe if your parent's an English teacher, give it to them. Or if they're in the sciences, have them read it, see if it makes sense. This section on the grammar, here we go. Third person passive past tense. So third person obviously is it. And passive is, well, it's better illustrated than it is trying to define it. So if I, during the procedure, if I actually went in and measured out 250 milliliters of a solution of some kind, I would say this, 250 milliliters, say, of 0.1 molar sodium hydroxide was measured using a, say, 300 milliliter graduated cylinder. Okay. So that's what I consider third person passive past tense. It says that's actually what you did. And that's what the report is supposed to do. Let's see. Appearance is fairly easy because all your reports are going to be typed. If you're a touch typer, so much the better. Procedures, are they in logical order? Numbered procedures are best, right? Because it implies a step by step. This is what happened. Data, need a section on data. Is the data accurate? And what I'll do is during the experiment, I'll collect data from you guys as you do your experiments. Analysis. Did you actually think about the relationship of each of the variables that are being investigated during the experiment? How are they related? That's what they mean by analysis. What I mean by analysis. Then conclusions and summary. I have reports that they turn them in and they have no conclusions, no summary. So I have a special case for them over here. It's called 0. Or if they don't put much effort into it, they might get 3 points. I've had some of them basically say, we had fun. Well, that's nice, but that doesn't have anything to do with the experiment. And then my overall impression of your report, do I think you understand what you're doing? Okay. Or are you just parenting? Understanding is what we're aiming at. Did the lab, doing the lab and writing the report is evidence. I worked for the government for 22 years in research. And one thing I learned for sure, among other things, is that if it's not in writing, it never happens. So that's the purpose of a report. And we had to do a report on ourselves, not this type of report, but a self-evaluation every 6 months. It was a pain to do it, but afterwards it was useful. Okay. So any questions on that? The actual report is underneath. So this is what I based this rubric on, this right here. So there's your title page, and you can see the structure there. It's got your name, your partner's name, if you have one. What's the course and the semester? And then I want at least the date that the experiment was done. If you want to put in a date for the lab report itself, that's fine. But I need the date that the lab was done. And then you see that the report is well organized. It's pretty. It's got headings and subheadings organized so that you don't have to search around for information. And the grammar is correct. Then the tables, right, are here. And this looks like there was some error in the data, right? Because I made corrections. Then there's a section on calculations, right? It's well organized so that I know what calculations are being done when and for what reason. So, and that also tells me whether I think you understand what's going on. When I look at the calculations, say, this is well organized, it's well thought out, it's logical progression, and that's good. Now, what do you do if some of these lab questions actually are just telling you to do something like do a calculation? That's the lab question. Well, when you get to that lab question, if you've already done the calculation in some other part of the report, you just reference that. You don't need to write the whole thing out again. Okay, and then there's a section on conclusions and summary. So looks like all the sections are here. Let's see, is there one on safety? Because there wasn't one in the notebook. Did the safety make its way in here? Yep, there it is. it's better if you put safety in your notebook, because it's better to be safe before you go in the lab than after. Okay. In fact, the best way to be safe in the lab is be prepared. That's one of the reasons that I want you to set up your notebook for every experiment, so that you've at least read through the experiment, read through the hard copy, and you know what you're going to do. That's the best way to keep from killing your lab partner. Okay, and then I hated to have to do this one, but I've experienced it before, is plagiarism. In the liberal arts like history and English, plagiarism is pretty obvious. You know, you just don't verbatim copy somebody's work and then not give them credit for it. But it might be a little more nebulous in lab reports. In this case, it would be obvious then if you wrote something that was completely out of grammatical character for you, and the rest of your report you write a certain way, and then all of a sudden, bam, it changes. And that's a clue that you've copied something off the internet. But then there's also the problem of lab partners submitting reports that are verbatim identical. They just slap their name on the other one. If that happens, all I can do, I don't know who it belongs to, you know, who actually wrote the report. Then what I do is I grade the report and I give one person half the value and the other person the other half. So if it's like 100%, then you get 50%, and the other person gets 50%. Or you have 3 lab partners and all 3 of them do it, you know, it goes down from there. But this helps identify what I consider plagiarism. So we're not going to hammer that one right now. I'm sure you guys are honest enough, you probably won't do it. It happens most often with spouses that are in the same class, or cohabitants that are in the same class. So if I know that in advance, then you can't be lab partners. We don't have any in here, do we? No. Okay. That's good. I didn't figure so with such a small class. Okay. So that's, all right. What other resources do we have before we actually get to the chemistry? Let's see. There. Oh. This is for you. This document right here is a table of extended character set commands. So on your keyboard, you've got your standard ASCII layout, not ASCII, but QWERTY layout of letters. And you've got some, you got numbers, and you've got some shift keys will give you special symbols, but they're not always the ones you need to write a lab report in the sciences. So some symbols like, for instance, plus or minus. You know, where do you find that one? It's not there. Or if you have delta, like we're doing thermochemistry, and you have a delta H for heat enthalpy, then you'll need that delta. Well, you can go into the character map that Windows has, if you use Windows, character map, and you can hunt it up, and you can select it and copy it and then paste it. But that's too many steps. If you look at this one, say the second column from the left, at the very top, there's a delta sign for under output. To the left is the code, 0916. If you hold down the Alt key and type in 0916 on the number pad, then this symbol will pop up. And simple, just that quick. If you use them a lot, then you'll have them memorized. If you're measuring something in micrometers, you need the micro symbol, the Greek letter mu. Just keep going down a little bit until you get to 0956. Do the same thing, up comes the mu. So you got 2 sets for Windows-based computers, the Win character and the DOS character. DOS is ancient. It stands for Disk Operating System. And that was before Windows. But apparently these codes are grandfathered into the the matrix of the operating system. So they're still there. So if one doesn't work, maybe the other one will. Now, if you have a Mac, I'm not sure if these Mac codes work because I don't own a Mac and I don't ever want to own a Mac. But some of my students who do says a few of them work that they know of. So if you have a Mac and you're interested, then check them out, see if they work. But I threw them in there just to show you that I'm not prejudiced, even though I am. I don't like Macs. I didn't like them when they came out as a kit back in the late 70s. You have to, in order to get an Apple, you go into an electronics store and buy a box kit and put it together yourself. Those were the first Apples. And then they were too expensive back then, even as a kid. And then when they started making them whole, they were still too expensive. Okay, so that's enough of my soapbox. Put this back here, there. Let's see. I guess we ought to go back to the, let's go back to the syllabus and see if I've missed anything. There's my schedule. Bonus and extra credit. If your grade's lagging toward the end of the semester, don't ask me for extra credit. Extra credit for bonus work I give to everybody equally. And I do have some of that. I've got a couple of exercises that I've handed out, and I'll point those out to you now. This one that says getting to know the periodic table. It's got instructions on the front page, and it's got a blank periodic table behind it. That's what you fill out with your code tables, and that's extra credit. Hopefully, it helps you learn things about the periodic table, reinforces them when the incentive is more points. Then, when we start naming compounds, this one is also extra credit. So it's got either the compound and you write the name for it, or it's got the name and you write the compound. And of course, you're going to need the rules to understand how it's done, so you don't want to just go home and try to figure it out on your own. But that's extra credit. Any other extra credit will be embedded in exams. Maybe the first exam might not have extra credit because all that stuff is absolutely essential that you learn. So there's no point in extra credit. But later on, I do add some extra credit because I realize that under the stress of the situation, your mind go blank on something. Happens to me all the time. So if you go to extra credit and say, all right, I know how to do that one, then maybe you can make up the loss in the rest of it. And your grade is based upon the required sections. The bonus, you can try them or not try them. You won't lose any points for trying. All right. Let's see, there's my schedule again. Okay, part 3. You can take that one or leave it. All right. They sprung this new format on us the week before class started. I said, thanks a lot. Okay. So we're going to get into chapters 1 and 2 in just a second. Oh, here we go. In order to talk chemistry, you got to know the alphabet. And there's the alphabet. Symbols. Symbols for the elements. And that's what this is for right here. Everybody get a copy of this one? It's probably buried in there somewhere. What you'll notice is I couldn't find any a periodic table on the internet that I could modify to satisfy me. So I just built this one in Microsoft Word. And you'll notice that some of them have red boxes around them. And actually they have sort of a pink tint to them, right? These that have the red boxes around them are the ones I want you to memorize. So each one of those symbols represents a named element. Upper left-hand corner, H is hydrogen. That's the easiest one on the table. Then over here on the far right is helium, He. Memorize those symbols for the elements. There are 118 elements in the periodic table, and I think 60, 61, 62 maybe of these I want you to memorize. So if you don't already have it, I mean, if you've had chemistry before, anybody had chemistry before? Yeah, so you probably got most of them memorized. You just need to refresh your memory. So I found the best way is flashcards. Make your own flashcards. Don't buy a set, because the act of making the cards is part of the memorizing process. So you put the symbol on one side and the name on the other, and you just go through them, right? So, yeah. Oh, got that one right. Put it over here. Got that one wrong. Put it over here. And you just keep going through it until you get all of them in the right stack. Then you go back and do it again. If you can go through the whole stack and get them all right, actually going through both ways. Maybe you shuffle them up. So sometimes you'll see symbols and sometimes you'll see names. If you can do it 3 times or more in the right stack with no wrongs, then you're pretty good to go. And besides, once we start using them, that'll reinforce it. That you don't have to memorize the atomic numbers. You don't have to memorize the atomic weights or the possible charges on the elements. That's what the periodic table is for. But we are going to look, we're going to see how it's organized. It's organized in a logical fashion such that you can take one of these neutral atoms and construct its electronic configuration. That is, where are the electrons? What are their energy levels? You can do that just by looking at the periodic table. Okay, so that's an exercise you need to do. And what else? I think that's it. So we can actually get to the meat of the topic now. I will point out, well, I always give you PowerPoints to go by, so you can scribble in the margins. Well, I have to print these in Beckley because they don't have color printers available here for us. Isn't that awful? Humans are color oriented. That's how we organize information. Oh, I forgot to mention this. For each of the exams, I created a review document. So it looks exactly like an exam, only it's a lot thicker than an exam. Lots of practice problems. So, and the reason I do that is because of your best friend. You have 2 best friends in chemistry, in this class anyway. Curiosity. If you always want to know more, if you study a topic and it sparks 2, 3, 5, 10 different questions, beyond that, you want to go find out about those, that's good. And the other friend is boredom. If you're bored working a particular type of problem, you probably know it well enough, you can move on. Curiosity and boredom are your 2 best friends. Now, I didn't print out the key. There is a key in Blackboard. It's just in red, it gives you the answers to each one of these. And if there are any, like here, fill in the blanks, they'll be there too. If the key helps you go, I have had students go through here and use this exactly like an exam. They just sit down and start going, you know, and then go back and grade it. And then that focus their energies on the ones they missed. If with that effort, you still can't understand some of these problems, then I created this worked problems document in my handwriting. I try to be as legible as possible. And this one is correlated with this numbering system, and it will tell you how, one of the ways at least, to solve that problem. And maybe if you are stumped one way, then look at this and see if maybe it makes sense. If that doesn't do it, those are the ones you bring to class on review day. And that's the first thing we do for review, is take the ones that are bothering you and work them. And only when we're done with that do I start a general review. Okay, I think I've covered everything except the PowerPoints now. So we can actually talk about chemistry. everything up to this point is more or less procedural. Okay. Oh, we didn't go into Blackboard. Are you familiar, comfortable with Blackboard? Okay. If you have any trouble finding stuff in Blackboard, just let me know and I'll talk you through it or show you. I try to make it as logical as possible. So I'm gonna pull this down, and we'll go into chapter 1. Let's see what time is it? 2 o'clock. So we've been here for an hour or more. Anybody need a break? Good. Okay. So I'll do chapter 1, and then maybe you'll need a break at that point before we go into chapter 2. So here is that. Okay. Let me check my picture here and see if it's picking it up good for that. Okay, yeah. That's it. I've had it, depending on the board that it's flashed on and so forth, it gets washed out. Yeah, everything that's here is there. Okay. I need my printer. I always pull the batteries out of this thing for some reason. It must have a short in it because it drains the battery to death. Okay. Let's see. That's right. So what is chemistry? There's a really general definition for chemistry. It's the study of substances. That covers everything and how they change from one substance to another. So you need ways to identify what is the identity of the substance, because if you don't know what it is, then you don't know if it's changed. But chemistry studies that. So that makes it a really broad central science, just like your textbook says. It's rather arrogant, actually. All other sciences feed into chemistry. Maybe it's true, maybe it's not. But there are a lot of sub-disciplines in chemistry. It probably has more than any other. Even organic chemistry is subdivided into types and sections. Like, you may an organic polymer chemist, like make plastics, stuff like that. Anyway, so it's going to help if you can develop some sort of intuition when you make an observation, a measurement, or a visual or other types of observation about a process that's taking place. Draw your attention to what's going on underneath the microscopic. Make a connection between the macroscopic and the microscopic, because chemistry is all about the unseen activities, right? Atoms and molecules. So eventually, if you do enough of this, you develop sort of an intuition connection between those two worlds. Think in the atomic level. So what is an atom? What's a molecule? Right? We got to get definitions out of the way too. Well, we know what matter is. From grade school, I knew what matter was. That by definition, it's anything that has mass and occupies space. That's matter. But we need more than that. And over the centuries, scientists have struggled with this concept and eventually come to the conclusion that matter is composed of elementary units called atoms. And atom is the word atom. It's interesting. Actually, John Dalton's atomic theory, his jumping off point was ancient Greek. The ancient Greeks, a few of them, believed that everything was composed of this elementary particle. And they called it an atom because in Greek, that means not. Anything preceded by a means not. And this is their root word for cut or divide or something like So it's not divided, it's indivisible. You can't divide it any further. So that's what they called an atom. They couldn't get a lot of the ancient, their scientific, philosophical brothers to believe in. But it turns out they were right, except they didn't go far enough. They believed that every atom was the same as every other atom, no matter what the substance. So then they struggled with, well, how come this rock is different than that log? If they're all made of the same stuff, so they had to come up with explanations for that, and that was a problem. But it was a start. Okay, so atoms are the smallest part of an element that's still that element. It retains the identity of the element. Now, the element can be 1, 2, 5 billions of atoms, but it has a characteristic that is distinct from any of the other elements in the periodic table. And it is that way because of the identity of each of the atoms. Now, when you put two or more atoms together, and it changes the identity of the substance, that has to take place by chemical means. They have to attach to one another. And now they're behaving as a unit. So oxygen behaves a certain way, hydrogen behaves a certain way. Water, which is composed of oxygen and hydrogen, behaves completely differently. Hydrogen is flammable, combustible, and oxygen will support combustion. So when you put them both together, they have a real party. Well, if you put them together in a container, then they won't do anything. They need a little bit of a kick. So a glowing ember or like a spark, then they're off to the races. The biggest race I ever saw was the space shuttle when it took off. The main engines on the space shuttle, they're fueled by liquid hydrogen and liquid oxygen. And they use that because it creates a lot of power. Their word for it is specific impulse. It's very high. So it gets you off the ground efficiently. Okay, so these molecules acquire a new identity. Now, the concept of the molecule doesn't have to be different atoms. Right? The oxygen molecule is actually like that. 2 oxygen atoms bound together. Those are bonds. And these are free electrons. Actually, not free electrons, but they're unpaired. Lone pairs, that's the word for it. They're lone pairs. They don't belong to any bonding. Anyway, that's a molecule. And that's a molecule. And this is a molecule. Right? It's more than one atom bound together. It doesn't matter if they're the same or different. We have another name for molecules that are made up of different elements. It's called a compound. Okay. When we write symbols, and the symbols, of course, are either single capital letters or capital letters and a small letter. And this system was proposed and adopted from a scientist named Berzelius. I'm trying to remember when he lived. 1700s, I think. There were a couple of proposals for how do we represent these elements? What symbology do we use? And I'm glad Berzelius won because some of the others were really wild. They were more akin to alchemy. Anyway, the symbol itself, and I'm going to use a generic here. There's no element on the chart that has a single X. There's an XE, but no X, so I can use that as my substitute. There are 4 positions here, 4 corners, and information is reserved for information. This is, if you have a charge, that's where it goes right there. So we say 1 plus, no, you don't have to say 1 plus, just say plus, 2 plus, 3 plus, 4 plus, or you can say minus, 2 minus, 3 minus, 4 minus, goes right there. If you have more than one of these atoms, then it goes here, number of atoms. Okay. For chemistry, that's usually enough. But if you're talking about nuclear science, if you need to say something about the nucleus of the element, then that information goes here. That's the atomic number of protons. And this would be the mass number. It's the number of protons plus the number of neutrons. Okay. So a chemical reaction is written, it's not written this way, it's written with symbology. Right? So you have water, right? Reactants, and then the products. Okay. Now that's not balanced. We'll talk about balancing the equation in a little bit. But the reactants on this side and products on that side, and arrow in between. Sometimes you can put information here for what's involved in the reaction. What did it require? Did it require heat? Right? And that's our symbol for heat. Or electricity. I'm not sure what the electricity would be. Because in order to get this to split into that, you can do it with heat, but it's more efficient to use electricity. Just a direct current, and you can split this water into hydrogen and oxygen gas. Distilled water works best, but probably any water would work. A little cup of water, a glass of water, about that deep, and maybe put a drop of lemon juice in it to make it conductive. Pure water is a non-conductor. So you need a little bit in there, and you can take a 9-volt battery and drop it in there. And pretty soon you'll see bubbles forming up the electrodes. So one of them has hydrogen coming off, and one of them has oxygen coming off. That's called electrolysis. It's not the kind where you get rid of your mustache. Okay, so now we're going to go back and be a little general now. Talk about science. Because all this information that we gained over the years about chemistry is a similar method was used for all of the sciences. Right? Physics, chemistry, even biology. And we can go back to the root word for science, which comes from the Greek. And in some cases it means truth, in some cases it means knowledge. Right? Since this is not a philosophy class or a religion class, we'll settle for knowledge. So, and the scientific method is simply a plan of action. How do we obtain reliable information and organize it? Because science builds over time. In fact, some of the most ludicrous theories that have ever been developed are now dead. And they're dead because the scientists who champion them are dead. They tend to live on, especially if the scientists had a good reputation. Then that lends weight to their theory. And even if the theory is bunk. Now, I see one that comes to mind is called the phlogiston theory. You've probably never heard of it. But they used it to try to explain why changes occurred in physical changes or chemical changes. And it was, I mean, looking back, I mean, it was just completely ridiculous. But at the time, it probably made sense, right, based on what they knew. But it's a slow climb. Science is a slow climb, and you have to have a method for winnowing out the chaff and getting to the meat of the subjects, the truth of the matter. As I always tell my students, nature just does what it does. It could care less whether we're studying it or not. So science is our way of running to catch up, trying to figure out what nature's about. The natural world behaves the way it does, and we try to create an understanding of it. And this is one of the ways we do it. Now, the other thing about science is, if you ever hear the expression settled science, you have my permission to slap that person in the face because they don't know what they're talking about. There's no such thing as settled science. Scientists are always skeptical of others. And That's good. When you publish your work in a referee journal, well, first it has to pass the editors. Right? So the editor makes copies of your article and sends it to reviewers. I haven't done many, but I've done some reviews. It depends on your discipline, what you spend most of your time with, and they find out about you and they send you an article to review. And I marked it up with my red pen and sent it back. So they can take my advice or not. But it's that critique. Go back. How did that happen? I went a long way, didn't I? I keep my thumb off of that. It's that critique of each other that keeps scientists honest. There have been circumstances, probably that you've already heard about, scientists that cheated, right? They falsified their research. Right? Their careers ended rather quickly. There have been others that actually made it to the publication point, and only after other scientists could not duplicate their work, or they duplicated it with more refinement, and they were able to figure out where those scientists went wrong in their publication. Cold fusion is a perfect example. Two scientists at, I think it was the University of Colorado, claimed that they had created cold fusion on the benchtop at room temperature. You know, the same type of stuff that occurs in the sun at billions of degrees and tons and tons of pressure. They claimed they had done it on the benchtop. Well, they were basing their research on neutron flux. They were measuring neutrons that they thought were coming from their experiment, but it wasn't, because the experiment was duplicated by other scientists and found that those neutrons were extraneous to the experiment. So those guys, their career ended pretty quickly too. And I hope that the editor that let them publish is gone also, because they're supposed to be the gatekeepers. Okay, so the scientific method looks something like this. It usually starts with an observation, right? Like I said, nature's just doing what it does, and you notice something that piques your curiosity. And you try to explain it. That's a hypothesis. You try to explain what it is in a sentence. You're saying this happens as a result of that. Or if I do this, then that. And you just make a statement. And then you devise an experiment that'll test your statement under controlled conditions as best you can to see if your statement is true. So that's what the experiment does. It tests this hypothesis. And then you analyze your results, right? Did the experiment support your hypothesis or did it not? Right? And it doesn't matter which way it went, because that's good information. It tells you if you were barking up the wrong tree, then go bark up a different tree. I think Edison, you know, the light bulb guy, he was approached by a reporter and said, I understand that you failed 99 times to make a light bulb. He said, I didn't fail. I just found out 99 ways that you don't make a light bulb. It only takes one to be commercialized and make a fortune. So you do that. And then once you've analyzed it, then you may go back and you may observe it again, or you could go straight into the hypothesis step and make another experiment. And you just keep doing that until you finally figure out the truth or the facts or the knowledge behind your observation. And when you do that, sometimes you're able to formulate it, either in prose or in a mathematical formula. This isn't chemistry, but it's a good illustration. Newton's first law of motion. An object at rest tends to remain at rest, right? Unless it's acted upon by an external force. Or an object in motion tends to remain in motion in a straight line unless acted upon by an external force. That's the first law, Newton's first law of motion in prose. That's all, it just says that. And the thing about laws is a law says nothing about why. It just says, these are the circumstances, this is what happens every time. He was right up to a point. His laws were useful But like I said, they're not settled. Because what happens when the object, the mass of your object that's settled or moving becomes very huge, like black hole size. Then Newton's laws completely fall apart. So along came Albert Einstein. And he says, okay, here's my theory. First, he went with special relativity, and then he expanded it to general relativity. That takes care of very large objects. What if it gets really small? You know, Newton's laws break down there too, right? You get to the atomic level or the subatomic level, you can't use Newton's laws down there. Now you need quantum mechanics. Right? So that brings me to the topic. Well, okay, before I do that, let's talk about theories. Once you've done enough of these experiments, you may devise a theory. And the difference between a law and a theory is a theory tries to explain why it happens. And the theory has a predictive quality about it. It says, if I make this fundamental change that the law doesn't allow, what's going to happen? Right? So, and it usually requires a model of some kind, either a physical model or a mathematical model, statistical model of some kind, that can be tweaked to see what happens when you make those changes. So the theory says why, the law doesn't say why. In fact, Newton struggled with his law of universal gravitation. I mean, it works. I mean, the force between two bodies, you have a proportionality constant, of course. And then you have the size of one mass and the size of the other mass. And then you have the distance between them. So that tells you something about how they attract one another. But that's just a law. It doesn't say why. He could never figure out why they attracted one another because there was no obvious, string attaching them to pull. So he just said, okay, it's because of action at a distance. So in other words, he didn't know. It took Albert Einstein to explain why. With his theory of general relativity, basically what he said was large masses curve space. And objects that are moving in that space, in the vicinity of that curved space, they follow the curve. So that's why the Earth revolves around the sun. The sun is massive enough to curve space-time. And now what would have been a straight line is actually following the curved space. And what's keeping us in that curve is a push, not a pull. So the curve of the space pushes the Earth into that orbit. Anyway, it's the predictive quality that makes theories so much more powerful. And we're going to look at some theories down the line. Dalton's atomic theory was the first attempt to explain how matter is composed and why it behaves the way it does. Was accidentally bumped that key. Okay, and with these predictions, you can also do experiments to test them, to see if the predictions are valid with these changes. So what happens is you've got a nice theory, and you do an experiment, and your theory falls apart. It doesn't even come close to proper prediction, right? We have three choices. One, you can restrict the application of that theory. Just say, under these conditions, can't use it. So Newton's laws of motion and his law of gravitation says it works fine for masses from here to here. But if they get too big or too small, can't use it. And in that case, we use a different theory, either Einstein's relativity or quantum mechanics. The other choice you have is modify. Right? Modify your theory to take into account the differences that you discovered here. And A lot of theories do that. They modify, 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 and eventually it gets so complex, you have to go to the third choice. Trash. Throw it out and start over again. Those are your three choices. Okay. So there's the law, this hypothesis, possible explanation for an observation in your theory in black and white. So eventually, in the sciences, qualitative observations, while informative, don't go far enough. We need quantitative, that is, measurements. And a measurement, initially, when you take a measurement, it always has a number and a unit of measure. So if I walk into a crowded room and I get everybody's attention and say, I'm 71. Say, oh, you don't look 71. They think I'm talking about my age, right? But what I meant was I'm 71 inches high. I'm tall, that tall. But it was my fault because I didn't put any units with it. So in sciences, it's even more important that you have a unit attached to the number that says how many of this size unit are they in that measurement. So the size of a Fahrenheit degree is about like that, and the size of a Celsius degree is about like that. So it makes a difference. Size of a meter is like that, a little over a yard. Size of a kilometer, huge. So it's essential that you include the unit. Now sometimes, particularly, well, you can make a measurement with an instrument that's designed to do something for you. Sometimes it makes multiple measurements, different types of measurements, and combines them for you before it gives you an answer. And in that case, it may spit out the answer in complex units. And this illustrates the point that whenever you have two units or more, and you multiply them together, you don't just multiply the numbers, you multiply the units also. So apparently, this unit of energy, the joule, and this unit of time, the second, were part of the calculation. And so the output is joule seconds. Okay, we have fundamental units. These are agreed upon by scientists. In fact, there's an oversight committee that standardizes these things. Right? The SI stands for International System. It's SI because it's French, and they do everything backwards. But mass, the standard of mass that is agreed upon and fixed, is the kilogram. So there's a platinum iridium cylinder in a double bell jar with an inert atmosphere somewhere in France. I think originally they put it in a cave because the temperature is stable. And if you have a kilogram, you think you have a kilogram and you want to standardize your measure, you got to send it to them and let them compare it. And then they'll tell you, well, let's see, your kilogram compared to ours is really 1.0000257 kilograms. So then use that calibration when you apply it in your laboratory. So that's mass. Length is, the standard length is a meter. Originally, it was a fraction of the distance between the equator and the North Pole. But not just any place. You had to go through the prime meridian. Like longitude is degrees east or degrees west of the prime. So the prime meridian goes through Greenwich, England. In fact, through the Greenwich Observatory. And that's the distance they use. And then they subdivided it until they got a manageable size and stuff like that. Nowadays, if you have the money and the instrumentation, you can generate an accurate meter with your instrument because it counts the number of wavelengths of a particular element's light emission in a laser. And then you can do the meter yourself. Time, you can do the same thing with time. You just need an accurate clock. So there are several atomic clocks scattered around the world, and they standardize them. Actually, they send out time signals, right? We used to listen to one when I was in astronomy, high school, I think. So we'd be out for observing meteor showers. And we get our sleeping bags and lay out on a clear night, and somebody would have a radio, and it would be tuned to the NIST, National Institutes of Standard Testing, their radio station, and it would send out these beeps, and it would say, okay, at the beep, it's this time, and then it would continue beeping. And that way, if you saw a streak from a meteor, you knew exactly when it happened and you make note of it. So they had amateurs doing that all over the country. And then they took them and they compiled that data to more accurately determine the origin of the meteors. So this time can be accurately determined. The second itself was grandfathered in. Second was around long before SI came around. So they were stuck with the second and they had to standardize it. Kelvin is the temperature. It's not such a mystery. The unit of measure for the Kelvin is the same size unit as Celsius. It just starts at a different 0 point. And we'll talk about that too later. Electric current is how much charge passes this point in 1 second. That's 1 ampere. And it's measured in coulombs. The amount of substance, we're going to use this one a lot, the mold. What strikes me as funny is this is the whole word, M-O-L-E, and this is the abbreviation. He's dropped E. Okay. So the mole is just a number of things. It's most useful when we're talking about atoms or molecules, or those small things. How many are there? Well, they're so small, something that'll fit in your hand might be billions and billions and billions of them. So you don't want to have to write out a number like that. So this unit allows you to identify how many of them there are with a more compact unit. And then the candela, we're not going to deal with this one at all. That's a measure of light flux, luminous intensity. Okay, so maybe the fundamental unit is not the right size either. I mean, if you're going to be looking at cells under a microscope, you don't want to identify them in terms of meters because it's like a meter is this big and your cell is that big. So use a smaller unit like a micrometer or 10 to the minus 6 meter. Here. Oh, wait a minute, this is mega. Here we go, micrometer, right there. 10 to the minus 6 meter. So if you have a micrometer, you measure something in micrometers. So we have 25 micrometers. We measured something that size. How many meters is it? Well, just take this right here. What does micro mean? It means 10 to the minus 6 times 25 meters. So we took this and put it right there. And you can go backwards and forwards. It's a good habit to get into, making these conversions. Particularly, I mean, you can do it longhand, but if you can do it in your head, then you can save yourself a lot of time and trouble. Because some formulas in physics and chemistry, the units of measure are prescribed. They have to be a certain amount. Probably because the proportionality constant is a certain type. And we'll talk about one a little later. When we talk about gases, we look at the gas laws, and the ideal gas equation is just that way. Okay, so these prefixes change the size of the unit of measure based upon what they mean. So you need to memorize these, particularly the centi, the milli, the micro, even the nano. Pico probably won't get to until second semester if you come back, because then you're talking about the atomic scale. The nano is a little bit bigger than that, right? Those fibers that they put in your exercise leotards, the nanofibers, they're on that scale, billionth of a meter. Okay, what's the difference between mass and weight? This is sort of a digression, but it's an important point. Mass is a measure of substance. How much is there? Now, if you think of it in those terms, if you know the mass of something, you know how much it is, then it's the same no matter where you are in the universe. So a kilogram on the surface of the earth is a kilogram on the surface of the moon. But the weight, I may weigh, well, I'm not there yet, but this, for argument's sake, let's say I weigh 180 pounds. Okay, on the moon, I weigh 30 pounds. That's a measure of force, and it depends on gravity, right? So Newton's second law addressed this problem, right? He said force equals mass times acceleration. Well, near the surface of the earth, how fast do things accelerate when you drop? Well, we use a special symbol, G. It's 9.8 meters per second squared, right? So you put that in there, and you put kilograms in here for the mass, then you know that the force is kilogram meters per second squared. But we give it a new unit. It's called the Newton. Okay, and it's helpful to see the relationship between these different units of measure and what they actually mean. Because if this enters into a calculation, if that force goes into a calculation, and the calculation has other units in it, other variables that are using these, then you won't be able to cancel them if you're using that. But if you convert it to this, then you might be able to cancel and come up with a better estimate. Okay, so mass and weight are not identical. They're often used interchangeably. And I do it myself. If I have a method, a lab experiment, I still say, weigh this much of that something, when actually you're determining the mass. And there's some instructors that they turn mass into a verb. Instead of saying weigh it, they say mass it. Okay, it doesn't sound right to my ears. Uncertainty. This is one that trips up a lot of scientists. I mean, even the career scientists. They're so focused on proving this some point that they tend to ignore uncertainty, or they tend to fudge it. Uncertainty is, it's embedded in every measurement you make. It may be for one reason or another, depending on which measurement you're making, right? If you're measuring length, maybe you're looking at it wrong. You're off to one angle. It's called parallax error. But you have to recognize that every measurement has error. Some measurements have less error than others. But we need a way to express that error so that when we're discussing it with other scientists, they know what we mean. So whenever you write a number, say like that, and you say this number to some scientist, whatever units, let's be consistent, let's say grams, then they know intuitively, they know if they're trained, they know that these three, you're claiming those are certain. There's no error in those numbers whatsoever. When I say 7 here, I mean 7 there. The last one is uncertain. So by reserving the last one for the uncertain, then it anchors the rest of them as certain. This is basically a guess. So how do we make that guess? Well, our measuring device will be calibrated. Many of them are like for marks for length or for volume. If you're measuring the volume in something like this, it'll have marks here like that. Wherever there's a mark, if that mark corresponds to one of these numbers, it's certain. Or if we have subdivisions, then you can go to the next digit and say that was certain. But if your liquid is in here and the bottom of the meniscus falls in between those lines, that's your guess. Okay. For example, there's a burette. If you know a burette, know what a burette is? Okay. The trick with a burette is to recognize which way the numbers move. Right? The small numbers are up here and the big numbers are down here. The reason for that is because burettes are designed to deliver a volume. So if you start at 0 up here and you deliver some, then where it stops is the amount that you delivered. But you have to recognize that when you go past 20, you're headed toward 21. You're not headed toward 19. Now, this is wrong compared to that. Notice that? If you look at this one, that one should be up here, maybe 19.8 in that region. But this over here is past 20. It's like 20.1 something. So these are tenths. That means this is still 20. You haven't got to 21 yet. So that's 20, and this is 0.1, but it's not 0.2 yet. So the guess is 20.15. I think it's 5. The 5 is the uncertain part. You know, maybe you think it's 0.13, but the last one is a guess. Okay, what's the difference between accuracy and precision? In the popular media, they're the same. Accuracy and precision. I hear precision used all the time as a substitute for accuracy. But in the sciences, they mean two different things. Accuracy, in order to determine accuracy, you need to know the true value before you make the measurement, or at least an accepted value. Sometimes you don't know the true value. So a lot of times, a group of scientists will get together and they'll exchange samples and they'll all make measurements. And then they'll report their measurements. And then they'll average those measurements together. Now, that's the accepted value for that sample. So whenever they analyze that sample, they know they can compare their measurement to that accepted value, and that's a measure of accuracy. Precision, you don't need anybody else. All you need is 2, 3, 4 different measurements on the same sample. And then the scatter determines precision. So if it's very precise, the grouping is very close. And if it's not precise, the grouping is way out here. So this is what it looks like in a dartboard. So where would accuracy be with this first one? Average these values, and it falls about right here. That's not accurate. Not precise either, because they're scattered all over the place. You ever seen the Mel Brooks movie, Young Frankenstein? No? Oh, you got to watch it. This is great. It's in black and white, but it was meant to be that way for the ambiance of the period. So I won't tell you about that because it won't mean anything. This one is not accurate, right? Because the average here is way off target, but it is precise. It's tight grouping. This is a tight grouping on the bullseye. So that's accurate and precise. So there's one we left out. Right? We got yes, 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 no, and no, yes. Oh, no, no. So we need no, yes. Not precise, but accurate. So what would that look like? Well, here's the bullseye. Then we got a dart here, a dart here, a dart here, and a dart here. So the average is right there. But they're spread all over the place. We see that a lot in agriculture. I was trained in soil science. And in the field, the variables are they're just horrendous. Weather patterns and everything, it's hard to control your environment So you get those wide spreads a lot in agricultural research. Okay, so how are we going to account for these certain and uncertain numbers in such a way that we can track them through calculations? That's really the important part. Because when you multiply two numbers together, what do you do with the answer? I mean, do you take the 9 decimal points that your calculator gives you? Right? That would be cheating. So we have this system, significant figures. Right? If you've never seen this before, these are the rules. Any number that has, first we identify the significant figures for the individual numbers. And then we have rules for what do you do with them when you put them together in a calculation. Okay, so this is first step. All non-zero numbers are significant. So in this number, you got 4 significant figures. Okay. Then there's the cases where you have zeros. There are 3 types of zeros. Okay, there's one on the far left, like this one. Those zeros are not significant. They're dangling out there by themselves. And for this number, actually, if you write the number like that, it's wrong. That's what I call an orphan decimal. Decimals on the left-hand side have to be bracketed by 0. And you can put that 0 out there because it's not significant anyway, so it doesn't matter. But it does matter to the fact that that decimal now cannot be confused with a period at the end of the sentence, something like that. Or if you're in Europe, it'd be confused with a comma, right? Because they're backwards. They use decimals for commas and commas for decimals over there. Okay, so that's leading zeros are not significant ever. Captive zeros are still significant. They're placeholders. They're there for a purpose. So they're riding piggyback on these significant figures on either side. So this one has 4 significant figures. How about zeros to the far right? It depends. Is there a decimal there? If there's a decimal, all of these zeros are significant. If there's no decimal, that 0 is not significant. So what if I made that measurement and said, uh-oh, that 0 is supposed to be significant? There you go. Now it is. Okay. All right. And then there's one other type of number. It's called exact numbers. These numbers have infinite significant figures. So when they enter into a calculation, you can basically ignore them. I mean, they've got as many significant figures as you need. And this type of arrangement is conversion factor. This equality leads to a conversion factor, and I'll show you how that works in a few minutes. And then there are counting numbers like 9 pencils or 10 crayons or whatever the case may be. Say how many teeth are in your head, 30, 36, can't remember. But they would be counting numbers. Okay, before we do that, let's take a look at exponential notation. Now, the authors of my book, my textbook, they equate exponential notation with scientific notation. They're not the same. Now, I'm not sure what your book does, but exponential notation can be, let's say if we have 3, 0, 4, 5. Let's see, do that, 0, 0, 0, 0. Okay. If you write this, and notice that these zeros are not significant because there's no decimal there, no explicit decimal. There's an understood decimal, but it's not explicit. If we write this like, if we store up this information, 1, 2, 3, 4, 10 to the 4th, and then what's left over, 5, 4, 0, 3, that's exponential notation. You've used an exponent in the number now. You converted it. And this is equal to that in size. But that's not scientific notation. Scientific notation says that this coefficient has to be between 1 and 10. So we would have to go further. 1, 2, 3. 3 plus 4 is 7. 3.045. That is scientific notation. And if you manipulate and you end up with a number here that's 10, it goes to the next one. So then it'd be 1 times 10 to the 8th. The advantage to this is twofold. One is you can express very large numbers or very small numbers in a compact form. And the other is kind of a fringe benefit. If you do it correctly, this says, okay, that number has 1, 2, 3, 4 significant figures. Instead of looking at it up here, I mean, you can do the same thing. Look up here, look down there. Right? 1, 2, 3, 4, these are not. But there, you can see it right off. All right, so we're also going to need to know how to round numbers. We're going to keep it simple. If it's 5 or above, the digit to the right here, if this is the calculation that you get here, 1, 2 significant figures, 4 significant figures. This rule, the first rule is multiply, divide. And multiplication and division just says you take the smallest significant figures and apply that to your answer. So if your calculator spits out this number, and it's okay to do that, but then you got to round to the legal numbers. You can keep 2 of them. So where do you go? You go 1, 2. We're going to round that one right there. This one's greater than 5, so now that one becomes 4, and you keep those 2. And then there's add, subtract. Add, subtract is a little bit different. Here we go. In add, subtract, you line up the decimals. And your answer has the least number of decimal values in it as in the operation. So I'm supposed to have there's supposed to be a line here. Just add them up, right? You line up the decimals, you got this number down here, and this one stops right there. So that means you have to stop right here. So that's 5, that means 7 becomes 8, and you get to keep that. So with add and subtract, the answer could have, see, this one has 4 significant figures, but it's derived from 3 plus 5. And so you can't tell until you do the calculation how many is in the answer. What if you have a number like this? And you add to it, let's see. Like that. Now what do you do? There's no explicit decimal point there. There's an understood one to be here, so that's why I lined them up that way. So if you add them together, now what do you do with it? Well, that's not significant. So there's where you draw the line. And that means this one has to be rounded to 199. But you need a placeholder. Otherwise, 199 is not 1986. There you go. So that's what you can keep from this addition. All right. Let's see, how are we doing on time? 3 o'clock. I think we got till 5 to do the rest of what's done. I hope I can finish. So when you're in the laboratory, what determines the accuracy of your measurements? Overall, the accuracy of your measurement is determined by the least accurate device in the sequence. So in this case, you got this one that's marked off in 2/10 divisions, and this one marked off in 200th divisions, 5, 6, 7, 8, 9. Oh, yeah, in hundreds, 200ths. So when you put them together, you would be restricted by the accuracy of that. Okay. Just a short thing on problem solving. If you, the first rule of logic is, if you don't know what the question is, you're never going to get the answer. So when you read a problem or when you're presented with a problem, you always ask yourself, what's the question? What is the problem? Know the problem very well, the question very well, before you go try to find an answer. I mean, just because you've been studying a certain procedure in one chapter doesn't mean that that's the end all and be all for the solution to the problem, because most sciences are additive. In other words, skills you learn back here, bring them forward and apply them. And then what's given in the problem? What information is given? Maybe not all the information in the problem is what you need. You might have to go out and get some other bits of information. Or some of that information is thrown in there as blue smoke, just to confuse. Word problems are, they're written that way. They're designed to confuse. If you don't actually know the subject well, then word problems are going to spin your head around. I never liked them anyway. It's just that they do serve a purpose. And then how do I use that information to get to the answer? One of the ways we solve problems in chemistry is dimensional analysis, which is a fancy way of saying keep track of your units. A lot of the problems in chemistry can be solved simply by working the units. As long as you don't violate any chemical or physical laws, of course. So in order to do these conversions, you need a factor that allows you to do the conversions. So for instance, we saw earlier that 1 inch equals 2.54 centimeters. That's an equivalence. We know that anything measured to be 1 inch is also 2.54 centimeters with a different unit. Okay, so suppose I have measured something as 25.4 centimeters, and I want to convert it to inches. So I want to end up over here with inches at some point. Well, you need something to multiply by that will give you inches. But you can't violate any mathematical rules, right? So we need to multiply this by 1. We know that that's true. If you multiply anything by 1, you haven't changed it. But that doesn't give our answer. So we need to substitute for that. Do we know something that is equal to 1? Well, yeah. If we do this, divide both sides of the equation through by 2.54 centimeters. Right? This is equal to 1, isn't it? Right? Something divided by itself is 1. So now 1 can go right there. So now let's put it out here explicitly. 2.54 centimeters and 1 inch. So there you have it. The equivalence becomes a conversion factor. Centimeters cancel because this is in the numerator, correct? Okay. So the centimeters cancel, leave us with inches. Now all you have to do is number crunch. So 25.4 divided by 2.54 is 10. Let's see. 3 significant figures. There you go. So that's why conversion factors work, because all conversion factors are equal to 1. And if you wanted to go from inches to centimeters, that's equal to 1. If you flip it, it's still equal to 1. So you just turn it however you need it. Okay. That's the type of dimensional analysis that we use most often in this class, is unit conversions. And here are examples. I'm not going to labor this point. You can look at it if you want. The point here is that conversion factors can be chained together. Since each conversion factor is equal to 1, then you can say this times 1 times 1 times 1 times 1. It's still valid. But you need different conversion factors equal to 1 in each place based upon the units that you want to cancel and the units that you leave behind. Okay. Oh, this is a practical example. Right? I don't know why I picked New York and Los Angeles, because nobody wants to go to either place anymore. But very often what I do is make the estimate for driving to Atlanta because I have family there. So what do I need to know? If I'm going to say I need a certain amount of money in my pocket so that I can buy enough gas to get down there, drive around, and get back. So I need to know what? How many miles am I going to travel? So to keep things simple, let's say Atlanta is a big place, so it depends on where you go in Atlanta. Let's say it's 400 miles from here. I think it's a little bit less than that, but 400 is a nice round number. So if I'm going down there and get back, that means I need 800 miles. But I'm going to drive around down there. It's a big place, so you got to drive 15 minutes to an hour to go anywhere. So let's say let's buffer it with 200 miles. So let's say I need to account for 1,000 miles. Okay, so what else do I need to know? Well, it depends on the vehicle I'm driving, correct? If it's an efficient vehicle, then all the better. But let's say for argument's sake that my vehicle gets 25 miles a gallon. I wish. I've gotten as high as 24. And then what? Well, you can use this to convert to gallons, but I'm talking about dollars. So what do we need to know? The price of gas. So then you can convert that based on the price of gas. And let's say it's more expensive up here than it is in between. Like go to Withville and you can probably save 20 cents to 25 cents a gallon. But by the time you get to Atlanta, it's back up again. So just for argument's sake, let's say it's $3 a gallon. With that information, you can say that's how much money I need to take. So how do you do that? Well, 100 miles and 25 miles per gallon. Right, so miles cancel. Now I need to get rid of gallons. So gallons goes on the bottom, dollars on the top. It's 3. And then this is 1 gallon. So that cancels, and now I end up with money. So I know I'm right with the units. The rest is number crunching. So you say 1,000 times 1 times 3 divided by 25 divided by 1. There's your answer. Okay. Let's say, well, we're going to talk about that's simple unit conversions where you only need a simple conversion factor. But sometimes the conversion is a little more complex than that. And that's true for temperatures. Fahrenheit and Celsius are related, right? Because nature just does what it does, and it gets cold and it gets hot. It's cold and hot. And we apply these measuring systems to it. But you're measuring the same thing. If you're using 2 systems, you're still measuring that same thing. So they've got to be related. So this is what they look like in illustration. Fahrenheit's like this. 32 degrees is the freezing point of water. 98.6 is body temperature. And in Celsius, 98.6 is 37 degrees Celsius. And 0 degrees is freezing point. In the interest of time, I'm not going to go into the historical significance here too much. Fahrenheit came first, then Celsius, and then Kelvin, historically speaking. Kelvin was derived from Celsius. So that means Celsius and Kelvin both have the same size degrees. So that's good. All you need to do with those is just shift the 0 point. You're good. But just shifting the 0 point between Fahrenheit and Celsius is not good enough because Celsius has a different size degree than Fahrenheit. So you need an additional correction. And this is what it looks like. For Fahrenheit, this is the way I learned it. Fahrenheit equals Celsius times 9/5 plus 32. So this corrects for the 0 point, this corrects for the size of the degree. And if you learn this one, you can calculate that one, right? Algebra, just solve for the unknown. Whereas Kelvin, since we shift the 0 point, Kelvin is absolute zero, is the 0 point. Can't get any lower. And that's why Kelvin is valuable, because there are no negative numbers in Kelvin. So if you add 273, and we're going to drop to 0.15, you don't need that. 273 plus Celsius, and you get Kelvin. Or if you have Kelvin and you want to find Celsius, just subtract 273. This is an interesting problem. Since they have different size degrees, Celsius and Fahrenheit, they've got different slope lines, and they're going to intersect somewhere. So I'm interested in where do they have the same value, both Celsius and Fahrenheit. So if we know the arrangement here, right, and this is supposed to be equal to that, just call them both x. So if there's x, solve for x, it's minus 40. Minus 40 degrees Celsius is equal to minus 40 degrees Fahrenheit. And I know what that feels like. I used to work in a hotel restaurant supply as a student. And we had to do inventory once a month. And we had dry goods, at room temperature. We had the cooler section. We had the inventory. We had a freezer section that was like at maybe minus, let's see, Fahrenheit would have been maybe at 0 degrees Fahrenheit. But I was a low man on the totem pole. I was a part-time worker as a student. So they blessed me with inventorying the blast freezer. So I'd have to go into this minus 40 degree blast freezer inventory product. So I go in for 10 minutes, I'd be suited up, 10 minutes or 15 minutes, and then I have to come out. Okay, density. The reason we've got this discussion of density in here is because of this formula. Whenever you have a formula like that, an equation, these three variables, if you know two of them, you can find the third one. That's true with any algebraic expression. If you know all the values that go into it, except for one, you can solve for it. And you only need one equation to do that. What are the units of measure? Well, it depends. Usually with solids, if we're going to density for solids, mass is going to be grams. And for liquids too. So liquids would be grams, solids would be grams. Solids, liquids. But the volume is usually different. Right? For solids, the volume is usually cubic centimeters. And for liquids, it's milliliters. Okay, thousandths of a liter. The interesting thing is, these are equal. Cubic centimeter and a milliliter are exactly the same. So if you get a solid that's, say, 10.5 grams per cubic centimeter, it's also 10.5 grams per milliliter, which is the density of silver. And the other point I'd like to make is the characterizing these variables. This is mass. This is a capacity factor. Or your textbook, if it has any discussion of it in there, may call it an extensive factor, which just means it varies with how much you have. If you have more of the substance, then this value goes up. So does this one, it goes up. But this value doesn't. No matter what how much you have of the substance, the density is always the same. So this is called an intensive factor, because it doesn't matter how much you have. All right. And this is just solutions to problems. And it's just like I said, you can solve for the unknown. All right, so matter occurs for our purposes in 3 different phases. So the same substance can either be a solid, liquid, or gas. Now, that's true for most substances. The problem is, for some, they may start out as a solid. You might be able to melt them into a liquid. But if you add too much temperature, they could decompose. You cause a chemical reaction before you get to the next phase. So you have to consider that also. And if you look at, let's see, what do you call them? My mind's gone blank. Handbooks. You look at handbooks of values for different substances. Like CRC handbook is a good example. There's just lists and lists and lists of, say, densities or melting points, those types of things. You look up these values. Sometimes for a substance under melting point, it may be blank or have a parentheses and a comment, right? Or have a little D, decomposes, or DEC, decomposes. Right? And generally speaking, gases, the molecules are very far apart and moving at furious pace. I calculated one of these in class one time, and these molecules were moving at greater than the speed of sound. Of course, they don't do it for a short distance for the smacking somebody else. The liquid molecules are getting closer together, but they're not held strongly enough. They just sort of slide past one another. That's why they can't maintain their own shape. The solids, they're rigid. They can hold their own shape. Okay. Now, let's talk about mixtures. When you put 2 substances together, and when I say substance, I mean pure substances. What do we mean by pure substance? Well, the substance has an identity, and if it's pure, it cannot be broken down into other substances by physical means. In other words, if we have pure water, you can't get it any simpler without breaking the bonds. Okay, and that's chemistry. Think when somebody says chemical reaction, always think breaking and reforming bonds. So if you get a pure substance, it could be a compound or it could be an element. But if you mix 2 or more of these together, they still retain their identity. The pure substances retain their identity, but now they're in the company of other pure substances. Those are mixtures. And they come in 2 flavors. Either heterogeneous, if they're mixed together and they're not uniform. That is, anywhere you look in that mixture, there's a different ratio of pure substances. Is heterogeneous. Homogeneous, on the other hand, anywhere you look is exactly the same ratio. So salt water would have the same ratio of salt to water everywhere you look. Now it's variable, right? You can have a lot of salt or very little salt, but once you've established it, anywhere you look, it's the same composition. We're going to skip over this because I'm talking too long. Physical changes are those which retain the identity of the substance. So you apply physical means, so you add heat, or you could even just separate by filtration, for instance, based upon particle size. You haven't changed the substances at all. That's a physical change. Boiling water or freezing water, you still got water. And we use these physical changes to separate mixtures. One way is distillation, like every moonshiner knows that one. You just distill your mash and you get the alcohol out of it. Of course, the first collection, you better throw it away because that's got the methanol in it, the wood alcohol. You give that to your customer and they go blind. So you take that first collection, toss it. Then you start collecting the good stuff. Filtration, of course. Chromatography is a fancy way to separate substances, and we don't have time to talk about it now, but it's a fascinating subject. And chromatography is a very broad analytical technique. It can be, you can do it, use paper, you can use columns of packed material, you can use thin layers of material. It's just sky's the limit. You can do it at low pressure, you can do it at massively high pressure. We used to operate a high pressure liquid chromatograph in my lab, day in and day out. Chemical changes. Now, when a chemical change occurs, the products have different identities than the reactants because you have broken bonds and reformed bonds. So water, break water apart, you break the bonds between oxygen and hydrogen, and then the hydrogens reform bonds and oxygens reform bonds. So those are chemical changes. This is just flow chart. You're welcome to look at it or not. Oh, I was going to say it's straight out of your book, but it's not. It's straight out of my book. But maybe your book has one just like it. All right, that's chapter 1. Does anybody need to take a break? I think maybe I better. Here's chapter 2. Let's see. So that I don't forget, run out of time doing it. What did we have to do today in the lab? Yeah. Safety, that's it. And then introducing graphing techniques. You have a copy of that already. Okay. So that's what we're going to do next week. You can read ahead if you want. We'll review chapter 1 and 2 and do that lab if you need to. Stick around. If you've ever graphed before, then this is going to be old hat. But it's something that so many students need. I've introduced it as a lab exercise. If you already know about graphing, then and you're familiar with Excel, it makes things easier. They draws the graphs for you. Okay, so review, and then the following week we'll have our first exam. And I have no lab scheduled for that exam, so we can take however much time we need. But if we can even, I will distribute the next lab, the laboratory techniques, and if we get an exam finished early and I get them all graded, then we can spend some time on next week's lab and talk about that a little bit. Okay. My utensils. Chapter 1 and 2 is for exam 1. So the next time we meet, we'll do review, chapter 1 and 2, and key off of that review document. All right. So, chapter 2. This is going to be a long recording. It's already 2 hours. We don't have to spend a lot of time on the history of chemistry. It's fascinating. I mean, the chemistry, you can trace it all the way back to the Greeks. They had their ideas about why things change from one substance to another. And all atoms were the same, but other influences change substances. Like what are the 4 basic elements? Earth, wind, fire, and water, I think. 4 basic. Then alchemy kind of took hold for quite a while. And it was more of a guild system. You train somebody with your knowledge, you can tell anybody else. So there was no incentive to share. The first chemist was Robert Boyle. He's considered the first chemist because he performed quantitative experiments. He made actual numerical measurements during his experiments and related various variables by numbers. Now, as far as chemistry laws go, I've talked about physical laws with Newton. I know those fairly well. But laws, remember, the laws just say what happens and say why. So we usually develop laws first. And then once we get comfortable with the law, as long as it works right over and over and over again, then we can come up with a theory, perhaps, that explains why the law works and go from there. Well, Lavoisier, who was a Frenchman, came up with this law, conservation of mass, and it just says that you can't make or destroy mass in a chemical reaction. If you start out with so much mass of reactants, all reactants included, your products are going to be the same mass. And within the limits of our measuring capabilities, that's true. Then along came Proust. I think he was French also. Came out with a law of definite proportion. And what that says is, it doesn't matter where the compound comes from. Once you identify a compound and purify it, whatever its source is, the source is irrelevant at that point. From that point on, that compound will have exactly the same mass ratio of elements. Right? So water would be 18.2% hydrogen, I think. And the rest is oxygen. Whether it's derived from the space shuttle engine or whether you purified it by distillation. That's the law of definite proportions. Then the one that sometimes gets mixed up with that one is the law of multiple proportions. The law of multiple proportions was proposed by Dalton. And all it says is that if you have a series of compounds, say with 2 elements each, then the ratio of these masses increase by whole number digits. Right? So if you establish that you've got this much X, say you pick the size of your sample so that you have 1 gram each of these. Right? Then this one is going, whatever this one happens to be, Y grams of this one. This one's going to be 2 times it, and this one's going to be 3 times it. That's the law of multiple proportions. Then you have to have a sequence of compounds with the same 2 elements involved. For instance, let's see, how about that work? That's acetylene, right? And then that's ethene, and this is ethane. Right? So you got the same amount of carbon, and each of these increases first by ×2, and then 2 more, 3 times. That's an illustration of the law of multiple proportions. So the law of definite proportions came first. Then Dalton came up with multiple proportions as an extension. Okay. Dalton, at the beginning of the 19th century, accumulated all the information that he had and all the information that he could glean from other scientists' work that he trusted. and he put together an idea of how these things were actually working. Why did these things work the way they do? Okay, now we've got a theory. Well, he started with the basics, right? Like the ancient Greeks is, each element is made up of tiny particles called atoms. That's the simplest particle of each element. Then he said the atoms of this element are different than the atoms of that element. That's where he diverged from the ancient Greeks. The atoms of one element are different than the atoms of another element. He didn't know how. You know, we didn't know. At this time, we didn't know about subatomic particles, or at least it wasn't disseminated well enough for him to incorporate it into his theory. But he did know that in some fundamental way, these individual atoms were different, and that's what made each element different. Then he said that chemical compounds are formed by combinations of two or more of these different elements. And the ratio is based upon the number of atoms, not on the mass. Up to that point, all they knew was mass ratio. Now he's given them a reason for the masses being different. Is that the ratio is based upon the number of atoms in each molecule of each element. And he said, during the chemical reaction, this is why Lavoisier's law, conservation of mass, works. Because in a chemical reaction, you just rearrange the atoms. Right? You don't create any, you don't destroy any, you just shuffle them around. And the products come out with a different arrangement. They give your products different properties too, based upon the arrangements. But the atoms are not destroyed, they're not created, they're just rearranged. Okay, that was Dalton. Let's see. Gay-Lussac did work before Avogadro. Avogadro's work was based upon Gay-Lussac, but Avogadro took it further. Gay-Lussac, probably Frenchman, measured the volumes of gases that came out of reactions. And he changed conditions, temperature and pressure, and saw what consequence there was from that reaction. Avogadro then took this work and hypothesized, which was borne out later, that for gases, we'll find out when we talk about gases later, I'll give you this again. But to define a gas, you need 4 values, physical values: temperature, pressure, volume, and how much of it is there. N is the abbreviation for moles. How much gas is there? So you know these 4, you can define the gas and its behavior. You can't actually define the chemistry of it, but you can define its behavior. So what Avogadro said was, if you have 2 containers, right? I didn't draw them exactly right, but if the volume of this one is equal to the volume of that one, and the pressure inside is equal to the pressure in each one, and the temperatures are the same. If all those 3 factors are the same, then each container holds exactly the same amount of gas. Okay, that's Avogadro's hypothesis. And what that did was that opened the floodgates for chemistry in the early 19th century. Up to that point, chemists only knew mass. Right? They couldn't relate. I mean, Dalton's theory was out there, but they couldn't apply it to their reactions. So university professors and their graduate students that were doing experiments were just lost. When something went wrong, Their reaction didn't work. They couldn't figure it out. That was a tragedy. But companies were depending on their chemists to keep their reactions going in the most productive fashion. And when they went wrong, they couldn't figure it out. Those companies lost money, and lots of it. So they got together in 1865, I think, in a place called Karlsruhe, Austria. There's a university there. So they all got together from all over Europe and said, we're going to put our heads together and figure this thing out. Why are our reactions going cuckoo and we can't figure it out? So they were there for 4 or 5 days, having meetings, eating and drinking. Probably a lot of beer in let's see, where was that? Austria. Okay, yeah. Or maybe it was in Bavaria. No, it was Austria. Excuse me. Anyway, they came out of there all scratching their heads. They couldn't figure it out. Well, as it turns out, there was I don't know if he was a student of Avogadro, but he was certainly using Avogadro's laws, his hypothesis, to work with chemical reactions. And he had published a paper. His name was Cannizzaro, in Italian. And he was out there. He was kind of low down on the totem pole, as far as prestige goes. So he just waited outside the meeting, and he was handing out reprints of his publication. And he gave credit to Avogadro for his work. And they, the people that were taking his reprints, they were gracious when they did it. They took his reprints away, and they went back to their respective companies and universities, and some of them read the paper. And light bulbs started going on all over Europe. Said, that solves everything. Now we know that how to determine how many molecules are in this one versus that one, and how the ratios work. All right, so they started with gases. They did their reactions with gases. And this relationship was telling them what was actually happening at the atomic level in their reactions. Now they could figure out they didn't need mass anymore. I mean, mass, they used mass. But this extra bit of information started solving their problems. And that's when the chemical industry in Europe really took off, once they figured out those problems. Okay. Wrong hand. Okay. So what Gay-Lussac was saying, and Avogadro picked up on it, was if you have 2 volumes of hydrogen and 1 volume of oxygen, you get 2 volumes of water in the gas phase. So this gives you a reaction ratio, like 1 volume there, 2 volumes there. And what does that mean in terms of reaction? Well, we've already seen the reaction, the way it was written, I think. Hydrogen gas plus oxygen gas yields water, and in this case, gas. So to balance this equation, I need 2 here and 2 here. So what does that say? 2 volumes of hydrogen, 1 volume of oxygen, 2 volumes of water. That's what Gay-Lussac said. And Avogadro picked up on it and said, oh, it's even deeper than that. So then he elaborated. 1 volume of hydrogen and 1 volume of chlorine makes 2 volumes of hydrogen chloride. So these ratios were giving you a clue for at least gas reactions of what these coefficients are. Okay, that's a graphical representation of this equation. Okay, so we need to know, we need more information. If we want to know how and why chemical reactions occur, we need more information about the individual atoms. Right? All Dalton could tell us was that they were elementary particles. I mean, that's it. They're different in some way, but I don't know why. So along came J.J. Thomson. He was an Englishman. And he started by postulating a sub-elementary particle that was present in every atom of every element. A negative charge. And he actually determined the charge to mass ratio of the electron. And how is it related to, say, the other elements? Like he said, okay, it's about 1,800 or so times less massive than the hydrogen atom. Okay. And he used a cathode ray tube. That was big in those days. You know, they were fascinated with electricity, and especially in societies. And they would have these static electricity generators you crank up, fill up a charge, and then you get a line of guests together, all dressed up in their wigs and finery, and everybody hold hands, and then the one person on the end would touch the charge, and it'd go through everybody, and they'd all jump. You know, have a big time. But scientists were actually using it to do research and found that the nature of the electron, as it came to be called, was negative because we had established at that point the bipolar nature of matter. You know, you could build up an electric charge of either positive or negative nature. And you could either bend it with electrostatic plates, or you could bend it with a magnet, you know, and if it was positive, it's bent one way, if it's negative, bent the other way. So Thomson postulated that this element, or this elementary particle, was negative. Well, Millikan wasn't satisfied with that. That's generally the way it goes with science. Say somebody's answered a question, the answer generates 10 other questions. Right? So he said, I want to know, you know, just what the mass of that particle is. So he used some mathematical calculations and devised experiments to measure the mass of the electron. And he did it. He repeated the experiment thousands of times, literally. Every spare moment he had when he didn't have teaching duties or didn't have to manage graduate students or whatever, he was doing this experiment on his own. And he determined that the mass of the electron was very small, 10 to the minus 31 kilograms. It's tiny.
A thin list of oil drops is sprayed into the top chamber. Oil drops acquire a charge from air molecules ionized.
That's a little. Let's see if I can turn that down. Let's go back. Start it over.
List of oil drops is sprayed into the top chamber. Oil drops acquire a charge from air molecules ionized by an X-ray source. When the voltage on the charged plates is adjusted properly, the drop can be suspended between the plates. Several measurements allow determination of the charge of a single electron.
Okay, so that's a schematic version of his oil drop experiment. But the oil drops are very small, so he needed a telescope to see into the evacuated chamber. You know, and he used oil because it had very low vapor pressure. So in that evacuated chamber, he said acquired from air molecules. Actually, well, maybe there were some air molecules in there because, you know, we can't create a perfect vacuum. But it was evacuated, and he could see through a glass with his telescope, and he could watch the drop and adjust the voltage. And by calculating what the voltage was, he could tell what the charge was. So he did this experiment over and over and over again, and some of them required more voltage, some of them required less voltage, and he found that the voltage differences were varied by a whole number of units, right? So he worked his way down to the very smallest one, and then he said, that's the one that has 1 electron. I gotta retake control. There we go. Now, Henri Becquerel, Frenchman, was working with radioactivity. A lot of people were at this time. The Curies were, Marie and her husband, working with radioactivity. They didn't understand how dangerous it was at that time. In fact, it eventually killed both of them. But before they did, they discovered these things, and they found that radiation comes in 3 flavors. At that time it did. There are other versions of radiation now. Not the kind on Star Trek. That's theta radiation. It's that. I don't know. You can take a shot and be immunized. That's kind of stretching it. But the radiation they were concerned with came in 3 flavors. They knew that gamma radiation, there was absolutely no mass involved. This was purely light. High energy light, gamma radiation. Right? Beta particles turned out to be very fast electrons. But it's just the difference is the source of the electron. The electron comes from a radioactive nucleus. It comes from the nucleus of an atom that's undergoing decay. Alpha particles, these are negatively charged, of course. Alpha particles are positively charged. They're, by comparison, very, very heavy. It's basically the nucleus of a helium atom. So it's got 2 protons and 2 neutrons. We'll have to find that later. But it's very heavy, and it has a 2+ charge. Right? So you got your negative matter, you got your positive matter, and light. And those are basically the 3 types of radiation that were known at the time. So along comes Rutherford, Ernst Rutherford, who was an Englishman. And he postulated that there were various theories floating around. And one of them that was common, by this time they knew that the atom, the neutral atom, of course, had a mixture of positive and negative charges, and they were equal. That the same number of positives as negatives, that's why it was neutral. So one model said that they're all scattered in there together in the atom, like we call it the plum pudding model. But Rutherford said, nah, I think that the positive charges, which is most of the mass, by this time we knew about protons. Right? We knew they were very massive compared to the electron. He says the electrons are out here somewhere, outside the nucleus. So it had a very, very, very dense nucleus with protons in it, and then the electrons were out here. So he devised an experiment to compare and say, all right, they both can't be right. So he did what we know now as the gold foil experiment. Let's see, we have a no, we don't. Okay, I'll describe it to you. Back up, back. There. So he devised the gold foil experiment. He said, he used gold foil because he knew it could be hammered very thin, you know, just a few atoms thick. and it would still hold together. So he put this gold foil right here, and he surrounded it with detectors, probably photographic film. Right? So he had these detectors spaced around here. He said, what I'm going to do is I'm going to fire a very dense particle at this gold foil. And he knew that the alpha particle was very dense. So he had this source in this lead container of radioactive material, and he fired alpha particles at it. Now, to make sure that it went straight, he used a collimator. So what you do is you have a slit there, or a very fine pinhole, and then you have another one lined up here, like that. So only the ones that are going straight are going to make it through both of them. So they're going straight. When they strike the atoms here, if it's a plum pudding model, everything's going to end up right here, right? Because the density throughout is the same. Right? It's just going to go straight through. It might hit some, but it won't matter. The density is so low, they're all going to end up over here. Okay? If the plum pudding model is correct. If his model, if the nuclear atom model is correct, then what you're going to get is occasionally, well, most of them are going to end up over here because it's all empty space, right? Except for that dense nucleus. If it strikes the nucleus, a glancing blow, you're going to get some over here, or here, or maybe some back here. And occasionally you get one that strikes dead on and it goes straight back. Most of them ended up over here because it's mostly empty space. But occasionally you got a ping over here, 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 here. That proved that his model is correct, the nuclear atom. So the densest part is in this nucleus and the electrons are out here. Okay, so now we're building a model of the atom that we can use to help us explain why atoms react the way they do, why elements react the way they do. Okay, so now we've identified electrons, protons. The problem is we can't account for all the mass of every element with just protons, which is where electrons, you can discount them. They don't worth anything. So we can't add any charge because if we do, we've got to add electrons. And then we can't do that. So it was postulated we need a neutral particle that's as dense as the proton, but not charged. So we created neutrons to fill that gap. And that satisfied the progression of elements as they get heavier and heavier. Okay, so the nucleus of the atom is very dense. That's where the protons and neutrons reside. And our abbreviations for them, we say E plus for protons, say E minus for electrons, and N0 for neutrons. So if it has that 0 there, you know it's a neutron. If it doesn't, you know it means moles. Okay. There's so many elements in the alphabet, so we have to make do with what we have. Okay. And the nucleus occupies such a small part of the atom here compared to the rest of the atom that's occupied by electrons. Now, concept of isotopes. Now that we know that neutrons are available, we also know that when we isolate an element and characterize it, every atom has exactly the same protons. In other words, if you have a certain number of protons, you know you have that element. So if we have, 8 we have 8 protons, we've got oxygen every time. You change that number to 9 or 7 or whatever, you got a different element. But we also noticed that some portion, once separated, we count the atoms, and technology is here to do that. We count the atoms. Some of them weigh 16. Right? If you have 8 protons, that's the atomic number, and 16 is the mass number. And say we don't have a charge, right? And there's only one of them, so we don't put anything there. So if you have 8 protons and 16 minus 8 neutrons, so you have 8 protons and 8 neutrons, you have oxygen for sure, but you have an isotope of oxygen that has a mass number of 16. Occasionally, you might have an extra neutron. So if you have an extra neutron, there, now you have 8 protons and 9 neutrons. Chemically, they behave exactly alike. But one is heavier than the other. Now, why do they behave alike chemically? When 2 atoms approach one another, what do they see first? Electrons. They see electrons, right, as they get closer. So the electron interaction is where the chemistry happens. Okay? So this oxygen, since it has 8 protons, if it's a neutral atom, it'll have 8 electrons out here. This one has 8 electrons out there too. So chemically, they behave the same. Okay, those are isotopes. Now, naturally isolated sample of oxygen, or any element for that matter, will have a mixture of isotopes. Most of them will have one isotope that dominates, and the rest of them will be minor components. Some of them may even be radioactive. So they're in the process of changing from this element to some other element. But many of them are stable. Here's sodium, for example. This one on the right has an extra neutron. Has 11 protons. And the reason I drew it that way, around a symbol, you have 4 positions that are identified and reserved for information. This is the information for protons. This is the information for mass number. This is for charge. And this is for number of atoms. Okay. If you only got one, you don't need that one. If you're not interested in the charge, you can throw that out. If you're not talking about anything nuclear, just a chemical reaction, then you don't need those either. Because if you have a symbol, it's automatically, you know how many protons there are. But if we're describing isotopes, we need to use that convention. Okay, there you go. Okay. If X contains 23 protons and 28 neutrons, what element is it? Just look at the table. I'm going to use this one so it's closer for my old eyes. And they're arranged from upper left to lower right, getting heavier and more protons as you go. So left to right, you'll add a proton each time you go from one square to the next. So all you have to do is follow along. 19, 20, 21, 22, 23. These numbers here are the atomic numbers, the number of protons. So 23 is vanadium. Okay? So that's vanadium. And it has 23 protons and 28 neutrons. What's the mass number? So 23 would be here, and the mass number is 51, right? Let's add those two together. All right. Now, when reactions occur, certain types of attractions are involved. Right? One type of attraction is called the covalent bond. The covalent bond is one in which electrons are shared between elements, as opposed to ionic bond, in which electrons are transferred completely from one atom to the next. When that happens, all you have holding them together is electrostatic charge. So if we have sodium and chlorine to make sodium chloride, an electron is transferred from here to here, makes this one positive and that one's negative. Right? And how do you know that? Because if sodium has 11 protons, it had 11 electrons, now it has 10 electrons. So the difference in charge is a +1. Right? The balance of negative and a positive is a +1. But chlorine starts out with 17, and now it has 18 electrons. So its balance is toward one extra negative. Right? So once that happens, you get an electrostatic charge, unlike attract, right? Positive, negative. That's an ionic bond. For things like water, where you're combining hydrogen and oxygen, that's not balanced. But you don't transfer electrons completely from one to the other. You just share them. And we'll talk about why that is, why that works. But that's the covalent bond. And counterintuitively, these bonds are stronger than those bonds. Covalent bonds are much stronger than ionic bonds. Okay.
Halogen atoms will combine to form single bonds. Atoms combine to share electrons, forming a covalent bond. The covalent bond is often shown as a link between atoms, although it is actually a sharing of electrons. The diatomic chlorine molecules maintain their bonds even if they collide with other molecules.
And remember, the chlorine at room temperature and pressure is a diatomic molecule. It's one of those right there. So chlorine gas is going to be Cl2. Here's your ionic bonds. And we have special names. Of course, a charged atom is an ion. But if it's a positive charge, we call it a cation. If it's a negative charge, we call it an anion. Just memorize it. I could make an argument for why they're called that, but I think it's simpler just to say if it gains an electron beyond its neutral state, it's going to go negative, an anion. If it loses, it's going to go cation. And it doesn't have to be just a single charge. It doesn't have to be +1 or +2. It could be -1, -2, -3. It could be +2, +3, +4 charge. And it all based upon the difference in how many protons, how many electrons. Now, you can never create an ion by changing the number of protons. What happens if you change the number of protons? You got a different element. Yeah. So you have to do all this charge thing with electrons only.
Water, on the left, is a molecular substance that exists as a liquid at room temperature. Sodium chloride, on the right, is an ionic substance that forms solid crystals at room temperature. Molecular water has covalent bonds holding hydrogen atoms to oxygen atoms, but there are no bonds between molecules, so they move freely in the liquid. The ions in sodium chloride are held together by ionic bonds, which restrict motion of ions in the solid crystal.
Okay. So the point of this is that covalent bonds produce molecular substances. And the covalent bond holds that molecule together. It behaves as a single unit. Whereas ionic substances, you've got positives and negatives attracting one another. And they, physically speaking, they behave independently. But when we represent them in a formula, that's not the physics of it. The physics of it is a matrix of positives and negatives. All the negatives will be surrounded by positives, all the positives surrounded by negatives, and they form a crystal lattice. This is a simplest whole number ratio of sodium and chlorine in that crystal lattice. Okay? It's not really a molecule. I just want you to understand that. You still got those charges. We just don't write them. How do you know if it's that and not a molecular substance? Rule of thumb, if the cation comes from this side, the anion comes from that side, you've got an ionic substance. The farther apart they are, the more ionic the character of the bonds. Okay. So if you have two elements that are from similar parts, and that usually means from this side. If you get two of these reacting, you're going to get covalent bonds in molecular substances, including hydrogen. We stick hydrogen over here just for balance. Hydrogen's kind of an animal of its own. It doesn't fit anywhere. But if you have two of these together, what you get there is a special kind of bond that we're not going to spend a lot of time on. It's called a metallic bond. And there are various theories as to why that works. But these are not covalent bonds between metallics. And the reason I say that the way I do is that the periodic table is divided in gross manner between the right of this pointer as I go down like that. Over here is non-metals, over here is metals. So most of the elements are metals. Okay, so if you have an isotope of this element, let's say, and it's charged, okay? It has 54 electrons and 78 neutrons. What's the mass number? The mass number is going to be the number of protons plus neutrons. So you've got to find out how many protons this represents. Can we do it from that information? Yep. You know the number of electrons, but you know that it's got a positive charge. So the number of protons has to exceed the number of electrons by 1, doesn't it? So we have 55 protons. And then 55 plus 78 is 133. So the mass number should be 133. By the way, what element is that? 55? Let's see. Cesium. Yeah, cesium. This is kind of a tricky question. Which of the following statements regarding Dalton's atomic theory are still believed to be true? Elements are made of tiny particles called atoms. Yeah, that's still true. All atoms of a given element are identical. Not anymore. Not with isotopes. They're chemically identical, but they're not identical. If that makes any sense. A given element always has the same relative number and types of atoms. same relative numbers. Oh, a compound always has the same relative number and types of atoms. That's true. That's what makes it that particular compound. Atoms are indestructible. Yeah, we know better now with radioactivity. Right? So those two are still basically true. Now, the periodic table, how is it divided? I showed you metals and nonmetals, right? So if you can see that red line right there, when you fill out your extra credit periodic table, you'll need to draw that line in there. It's also divided into groups or families, right? So groups are vertical. So here's one group, here's another group, here's a 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 group. These, some of them have names, right? The noble gases, of course, are here. These are halogens, right? So let's see, a lot of cars use LED lights now, but there for a time, halogen bulbs were big. And I think they had iodine in. And then these are the chalcogens, named for combinations with oxygen. These are the pnictogens, starts with a P, P silent, P-N-I-C-T, pnictogen. Then over here we have the alkaline metals and the alkaline earths, or the alkaline earth metals, sometimes they're called. Then this group right here in the middle transition from one side to the other, so they're called transition elements. And then down here we have the lanthanides, based on the first element in the group, lanthanum, and it's extracted from this place right here and brought out here. The reason for that is, if you stuck it in there where it's supposed to be, periodic table will be huge. So we just pull it out here, along with the actinides. So actinium is here, and then everything behind it, when you get to the end there, and you can go back to this one, 103 to 104, and continue. Periods. The periods go from left to right. They're horizontal. Okay? And the reason they're called periods, let's see, has anybody had physics? Have you ever heard of something called periodic motion? Periodic motion is motion in a physical sense, but it's motion in which the object goes someplace and comes back. So it goes through a period of time, it goes out here and it comes back to here. It starts all over again. So the period here is it goes down to one end and it has to start all over again. So it goes down here and starts over again. And it goes down here, it's got to start all over again. Right? That's a period. A good example of periodic motion is the pendulum. It moves, but it comes back to the same spot each time. Same spot. Okay, okay, so here's the division between metals and nonmetals. We've got names here. It doesn't name these right here. The carbon family, the boron family, they don't have special names. Now, in reactions, when you find an element in a compound, if it comes from the alkali metals, this first group, it's going to have a +1 charge. And you can see up here in the upper right-hand corner the charge that's assigned to it. The alkaline earths have a +2 charge. Okay? It's important to know that when we start naming compounds and writing compounds, so that you know how the charge is balanced. Oh, it's on this page too. Then you skip over these because for some, the reason will become obvious later. Skip over here, these are +3, +3, +3, +3, +3, +3, at least for those. Okay. Then that's the alkaline metals. Halogens are -1. When they're combined in an ionic compound, they're always -1. Right? The reason they have other charges in here are not necessarily because those are charges, they're referencing something else called oxidation state. We'll have to talk about that later. So for our purposes, these are all -1. These are -2. These are -3. Carbon can go either way. It's kind of halfway in between. It can go +4, -4, or in between. It depends on what it's combined with. Okay. Naming compounds. We're going to start with binary compounds for naming purposes. Just to differentiate between the types of compounds, or among the type of compounds. If you have 2 elements or 2 components with opposite charges, you have a binary compound. The reason I say it that way is it's obvious that this is a binary, right? But sometimes you have polyatomic ions that behave as a single unit. So you could combine sodium with carbonate. This behaves as a single unit, that. So this becomes a binary compound. That against that. Sodium still has a +1 charge, but carbonate has a 2- charge. Okay? So that means in order to balance it and make it neutral, you need 2 of these, right? 2 times +1 is +2, balances the 2-. Okay. Binary ionics. Typically, a metal and a non-metal will make a binary ionic. And the farther away they are, the more ionic the character. Like if your cation comes from here, anion comes from there, that's definitely a strong ionic compound. If they come from the same side, both nonmetals, then you have a covalent compound. And like any definition, there are exceptions or there are gray areas in between, right? So in between these two, as the elements get closer to one another, they assume more covalent character and less ionic character. But for now, this will hold true, and particularly for naming them, it holds true. So, we're going to start off with naming type 1 compounds. Type 1 binary compounds have a cation, which is named first, and an anion, which is named second. And the cation is monovalent. That means that it only has one possible charge. Right? So it's going to come from either this group, that group, or this group right here. U +1, +2, +3. Okay. And the anion will have whatever its charge happens to be. It would come from this group, it'd be -1, so forth. But the key is, for type 1s, the cation has only one possible charge. Okay? The whole scheme of naming compounds, nomenclature, is to name the compound in an unambiguous way. You don't want ambiguity, because if you do have it, then you could write the compound in 2 or more different ways based on the name. You want to be able to write the compound in its formula based on the name, and that's the only way you can write it, based on the name. Right? So, for example, let's go back to this one. That has a plus, minus, so you have 1 and 1 only. So you just say sodium with a cation, and you change the chlorine to chloride. Just change it to IDE. Now we know that if we have this name, the only way you can write it is that symbol and that symbol. This was always +1, always -1. You only need one. So that's the only way you can write it. It's unambiguous. Let's take another example. Let's say we have aluminum. Let's say we write aluminum oxide. Bauxite ore. That's what you use, that's what you make aluminum from. Aluminum oxide, is that going to tell us everything we need to know? Yep, because aluminum can only be a +3 charge. And oxide, in this case, is only a 2- charge. Right? So how do we balance those charges? Cross multiply. Take the 2 down here, 3 down there. Check yourself. 3 times 2 minus is 6 minus. 2 times 3 plus is 6 plus. Balanced. Okay? Those are type 1 compounds. So, there are possible cations in there that have multiple charges. So what do you do then? Well, you go to type 2 compounds, in which the cation can have more than one charge. So when you name this compound, you have to specify in the name what's the charge. Right? So any of the other elements, and most of those elements will come from transitions or down here is metals. And when we name the compound, let's take an example. Fe2O3, right? Iron, oxide, but we have to say what's the charge on the iron. So you have to calculate what the charge is. So we know that oxygen is 2- always. So that means it's a 6- total charge, because you have 3 of them. So you have to balance that with 6 plus total from the iron. But you got 2 irons, right? So each one is worth a 3 plus, right? You just put a Roman numeral in there for the 3 plus. Okay? And with that name, you can write that compound. Right? You just say, okay, iron is this, and oxygen's that. We know this one's 2-. That tells us the charge here. So cross over Fe2O3. Okay? That's a type 2 compound. Okay. Now, when you start looking at your periodic table, you're going to find that there are a few, just a handful, of elements in here that only have one charge. Silver's one of them. So technically, you could use silver in the type 1 format. But rather than make you know the difference between the two, I just say if it's a transition metal and you write it as, say, silver chloride, you say AgCl, silver chloride without the 1 in there. I'll accept it. Because technically, there's only one possible charge, so it's type 1 compound. But since it's come from transition metals, you could say Ag1. You could say silver 1 chloride if you want. Okay. Polyatomics. Let's see, did we get them all done? No. We're going to do polyatomics first. There is, I think in your review document, there's a chart in there with polyatomics. Polyatomics have only one possible charge for each of those groups. Okay? So, this example of a polyatomic is OH, hydroxide. And the name for the polyatomic doesn't change. NO3 is nitrate, period. Actually, it's NO3 minus is the polyatomic nitrate. Sulfate is SO4 2 minus. It's always sulfate. So you don't have to change the name. You don't have to say "ide" or anything like that. You just put it in there as is. Let's try one that's not on there. How about this one? Okay. Do you treat this one as a type 1 or a type 2? Type 1. Potassium comes from alkali metals. It's only one possible charge. Right? And then you look up PO4. How do you know that that's a polyatomic and not a combination of 3 different elements? Well, one clue is that you have 3 or more elements. One of them is oxygen. If you see an oxygen in there, suspect polyatomics. Go look for it. See if it is. PO4 is a polyatomic. And you'll see from your chart, it has a 3 minus charge. And that balances 3 pluses with 1 3 minus, because this behaves as a unit. Okay? So we would say simply potassium phosphate. That's it. Type 1 compound. Now, what if we need, oh, here we go. Let's do it the other direction. Let's say I have magnesium phosphate. Let's write the compound. Okay, magnesium, Mg, phosphate, PO4. This has a 3 minus charge. This has a what? 2 plus charge. And that's all it is. So it's a type 1. So how do we balance the charges? Well, we need to take this 2 over here and this 3 over here. But we can't separate these right here. They have to behave as a group. So you put a parentheses around it. So it's 2 times this 3 minus. Because that 3 minus belongs to the whole group, not to individual atoms. So 2 times 3 minus, 3 times 2 plus balances. Any questions so far? We're covering a lot of ground.
To work out the formula of an ionic compound, we first select a cation and an anion. Some possible cations are shown here in blue, and some possible anions are shown here in red. Note that the anion might be an oxoanion or other polyatomic anion. Suppose we choose the sodium ion with a +1 ionic charge as the cation, and the phosphate ion with a -3 ionic charge as the anion. What is the correct empirical formula for sodium phosphate? Now we can select the number of cations and anions we want to use to build the simplest formula for sodium phosphate. If we select 1 cation and 1 anion, we note that the sum of the charges is -2, so the formula is not constructed properly. We must obtain an overall charge of 0 to have a correct empirical formula. If we add another sodium ion, so that there are 2 cations and 1 anion, we note that the sum of the charges is -1. Therefore, the formula is not constructed properly. We must obtain an overall charge of 0 to have a correct empirical formula. If we add 1 more sodium ion for a total of 3 sodium ions, we obtain charge balance and a correct empirical formula for sodium phosphate.
There you go. So that, excuse me, that 50 ways to name your compound, that other extra credit, should give you some extra practice also in naming compounds or writing compounds from their names. Okay, last one.
type 3 compounds. These, the first two were ionic. The third type is covalent. So these are compounds that are formed between two nonmetals. Technically speaking, they don't have charges, right? Because they're covalently bound. Right? So, but we're going to use the binary ionic compound convention to write them. The trick is to figure out which one simulates the cation and which one simulates the anion. Well, if you're working from a name, it's given to you. Right? You're given carbon dioxide. So automatically, this one is considered the cation lookalike and the anion lookalike here. But with type 3 compounds, since you don't have a charge, you have to say how many of each element is in the compound. And this name does. We don't say one or mono for this one, because if you got the name, I mean, there's always one. By convention, if the second one is only one, you will say mono. So you could have, this is carbon dioxide, you could have carbon monoxide. This is the friendlier one. This is the deadly one. Okay. So writing out carbon and oxygen, but you need two of them. Okay. That's it. It's all done. This one you need one carbon, you need one oxygen. That's it. All done. Okay. Now if we go the other direction, let's say, let me think about a compound. A type 3 type compound that would suit. How about two nitrogens, three oxygens bound in a single covalent molecule. Right. So we got nitrogen, but we have two of them. So we say di. That's the Greek prefix for two. And oxygen, we say oxide, but we have three of them. So we say tri. Dinitrogen trioxide. And I think your book or somewhere you should have, let's see. Oh, here we go. The prefixes for all the for 1 through 10, that's all you're going to need. They go a lot higher than that, but we don't need it. So there's your prefixes. You need to memorize those so that you know what they mean. Mono, di, tri, tetra, penta. Those are pretty easy. Then when you get down here, maybe you might get these two mixed up. Those are your prefixes. And examples, but we're running out of time. Okay, now, here comes a fly in the ointment. Acids came along before the naming conventions. So we sort of had to bend the naming convention to accommodate them. First of all, what's an acid? How do you know an acid by its formula? It has a hydrogen in it. Starts with a hydrogen, and then something else behind it. So in the first example, if you combine hydrogen and chlorine, if we name this by our previous convention, hydrogen's +1, chlorine's -1, so we would say hydrogen chloride. And that's valid if it's a gas, which it would be, unless you dissolve it in water. If you dissolve it in water, then you're making an acid. Because in water, this hydrogen
actually all of those hydrogens, will transfer to a water molecule. And in that case, if it's, no, not liquid. Not liquid. Aqueous. AQ. Means it's an aqueous solution. Then we have to name it with the acid convention. Okay? So, if you have this part of the atom attached to, the molecule attached to a hydrogen, and there's no oxygen, then you start the name with hydro. Always. If there's no oxygen, you say hydro. Then you take the element name and change the ending to ic. Instead of I, you change it to ic. So we say hydrochloric. And then follow with an acid. So dissolved in water, it's hydrochloric acid. That's the first convention. No oxygen. Here's one that's made from a polyatomic, CN, the cyanide ion. Okay, so CN minus 1 plus hydrogen makes the acid if it's dissolved in water. And that's hydro because there's no oxygen, cyanic. Instead of cyanide ion, it's cyanic acid. Hydrosulfuric acid. The ending here changes just a little bit. Rather than sulfide to sulfic, it just didn't flow. So we'll say sulfuric. So hydrosulfuric is H2S, dissolved in water. Right? If it's not dissolved in water, then you get white sulfur springs. Stinky water, hydrogen sulfide. Okay, what if you do have oxygen? If there is oxygen in the part of the molecule that's not hydrogen, then you don't say hydro. Hydro's out, no hydro. What you do is you take the polyatomic, normally what's what it'll be, and if it's NO3, the polyatomic is what? Nitrate. 8s become X. So nitric acid. That's it. What if it was NO2 minus? Right, if you look on your table, you find that NO2 minus is nitrite. So it's the nitrite polyatomic, and ites become us. So that's nitrous acid if it's HNO2. Okay. Then you've got sulfate, 8 becomes X, sulfuric. There's also an SO3. Right? And SO3 is sulfite, so it'd be sulfurous acid. This is acetic acid. Everybody knows acetic acid. Eat a sour pickle. Or you clean up cat pee like I do. You spray it with vinegar, neutralizes it, then you can clean it up. But C2H3O2 in that table would be the acetate ion. So 8 becomes X, it's acetic acid. Okay? And you have to balance the charge, right? So SO4 is 2 minus as a polyatomic, so you need 2 pluses from hydrogen to balance it. Let's see. All right, there's one other trick so that you won't have to memorize so many. There are some groups of polyatomics that make acids, and they're like in a homologous series, we call them. Right? One of them is chlorine. combined with oxygen. So I start with this one, ClO3 minus. This is chlorate. Right? So if you add hydrogen to that, it would be chloric acid. Right? If you add an oxygen, then it becomes perchlorate. And then the acid from that is perchloric acid. You take away an oxygen, notice it's still -1 charge. Then you have chlorite, and the acid that forms it from it is chlorous acid. And we go one more. ClO minus is hypochlorite. So it would be hypochlorous acid. So there you have a series of the chlorine, the halogen oxide to make your acids. And you can do that with 2 other halogens. You can put bromine in there. You can put iodine in there. So if you put bromine in there, it'd be perbromate, bromate, bromite, hypobromite. So you can get a lot of these just out of this one series. Once you learn that one, then you can replace these with bromine or iodine. So periodate, iodate, iodite, hypoiodite. And you can make acids out of them that way. So that saves you a lot of memory work once you learn one of them. Let's see. We only got a half hour left. Let's see. This is almost the last one. This is the last one. Okay. So just take a couple of minutes. Which of the following compounds is named incorrectly? How about potassium nitrate? That would be a type 1 compound because it doesn't have a Roman numeral in it. So it should say that we have 1 potassium and 1 nitrate because this is +1 and that's -1. That's correct. How about TiO2, titanium oxide? Is that Roman numeral correct though? Remember where titanium comes from right here. So it will probably have a Roman numeral. So oxide is 2-. And if we say titanium 2, that means the charge on titanium is 2+, right? So that means 1 titanium and 1 oxide will cancel the charge, right? But we've got 1 and 2 here. So that means titanium is actually a 4+ charge. Right? So that was wrong. Should be Roman numeral 4. OH is a -1 charge. So if it balances 4 minuses, this one needs to be a +4 charge. And it is. PBr5. All right, so where do they come from? That's the first question you ask. Are they metal, non-metal, or are they non-metal, non-metal? Right, so phosphorus is here, bromine is here. They're both non-metals. So this is going to be a type 3 compound. So really all you have to do is say 1 phosphorus and 5 bromine. That's true. Calcium, CrO4 is a polyatomic ion. See that oxygen in there? Should say, better look for polyatomics there. Calcium is a +2 because it's an alkaline earth, always. And chromate is a 2- charge, so it only takes 1 of each. It's raining. So the only one that's wrong is that one. Okay. So much for that brain frying lecture.
I'll let that run for a few minutes. case we need to pick up anything from the lab. Let's see. I already handed out your lab, didn't I? I didn't. Did I hand out the safety document? I didn't hand out the safety contract, did I? No, I didn't. Okay. I still need to pick up your and them all in together. So, right in here. Okay, so what I'm looking for here is just a recognition of these rules for safety purposes. Rule number one is know what you're doing before you walk in. Know the experiment before you walk in. That's one of the reasons that I had to fill out a lab notebook. And if you do the lab notebook, then you have to think about what you're putting in there, think about the experiment coming. Don't eat, drink, chew gum in the lab. If you have a drink, you can bring it in the lab, but put it up next to the chalkboard on the teaching bench. Okay, so it's away from the experiments. Then you can go access it whenever you get thirsty. That's where I put mine. Everybody knows not to fool around in the lab. Let's see. When you bring your stuff into the lab, be sure and stow it away somewhere where nobody will trip on it, like under the bench would be a good place. Or you could put it up in the front of the lab where your drink is. Let's see, those are the major ones. Always pay attention when you get an experiment or an exercise to do. Pay attention to the safety cautions. There'll be cautionary words in there for safety concerns, and you're going to include those in your written report anyway. When you do a formal report, there'll be a section in there for safety. And we'll talk about that more next time. So go ahead and, if you haven't already started, you notice there are two copies. One's for you and one's for me. So tear the back copy off and give it to me with your, that student number, that's not a telephone number, that's your student ID. So what is it in right here? It starts with an S, doesn't it? And besides that, name, telephone of your contact, we need to know if you have any medical concerns that we need to watch out for. Like, are you diabetic? Are you epileptic? You know, stuff like that that could put you in danger in the lab if we don't know about it. If you have any serious allergies, you don't have to worry about latex. All our gloves are nitrile. And then next week we'll assign buckets. We have a bucket assigned to each group. It's got some basic glassware and instruments in it. And then the other stuff is either under the lab bench or I'll provide it for each lab. Okay. So where does this go? Yeah. All right. Throw these away. Until next time. And shut this down. Keep my flash drive out. Turn this off. And turn that on. There you go. Okay. Is your brain humming? How many have had chemistry before, like in high school? Or? Oh, good. No?
I was a sophomore in high school last time. But
Okay. Hopefully it'll come back to you.
I hope so, yeah.
At least in the beginning, symbols, you relearn the symbols, and then you're off and running. That's most of the memorization. There's a little bit of memorization along the way. Most of it is learning how to solve problems. So let me stop this. So we talked about ionic bonds. Now let's talk about covalent bonds. Basic difference between ionic and covalent is the two atoms in a covalent bond don't want to give up their electrons completely. They'll share them. So for something like well, that earlier when I was talking about nitrogen and oxygen, right? When you put nitrogen and oxygen together, they pull on electrons in such a way that they won't give them up completely. So they share. So the bonding between these two elements will be shared. That's called a covalent bond. And there's your ionic bond. I've already talked about that. Now, we have special names though. If it's a positive charge, it's called a cation. If it's a negative charge, it's called an anion. Just memorize them. Okay. All right, so here's a test. Say you have a certain isotope that has a positive charge. So this isotope has one positive charge, and we know it has 54 electrons, and we know it has 78 neutrons. Okay? What's the mass number of that isotope? Well, if it has 54 electrons, but it's got a positive charge, let's look at it this way. If this were neutral, how many protons would it have? 54, right? If it were neutral. But it's got one positive charge. So it means it has to have an extra proton, an extra positive charge to make it that ion. So that means it actually has 55 protons, right? The difference between 54 negatives and 54 positives is one positive. So now we know it's 55. Added to 78 is what? 133. That's the mass number. Yeah. Okay. Oh, by the way, what element is that? 55 protons. Let's see. Let's see. 54. Cesium. So we would write it this way. Cesium. 133 and 55. Okay. Now there are other isotopes of cesium. It would change this number right here. Okay, let's look at John Dalton's law with what we know now, especially referencing isotopes. How many of the precepts or the postulates of Dalton's law, atomic theory, not law, a theory, are still true. Elements are made of tiny particles called atoms. Yep, that's still true. That hadn't changed. All atoms of given elements are identical. Nope, they're not, because we know about isotopes now. How about a given compound always has the same relative numbers and types of atoms? Yep, that's still true. And atoms are indestructible. Nope. Chemically, yes. You cannot destroy an atom chemically, but nuclear means, oh yeah. Just talk to Hiroshima and Nagasaki about that one. So those are still true. Now, the periodic table, we'll start looking at the periodic table. How is it organized? And this is where you get practice in that extra credit, organizing the periodic table. Major divisions, in this case, metals and nonmetals. So metals are generally over here on the left, nonmetals on the right, and the dividing line is this red line here. It goes like that, like that. It's kind of a zigzag. It starts out and goes between boron and aluminum and then makes a stair step all the way down. On the right is nonmetals, on the left is metals. Except, remember I said what I said about nature just does what it does? When you get close to that line, sometimes silicon acts like a metal and sometimes it acts like a nonmetal. So a few of these are classified as metalloids. It depends on their environment as to how they behave. And we take advantage of that with silicon, and that's where our semiconductor industry comes from. We dope it with different types of elements on either side and change its conductive characteristics. Then we put those two or more layers together and control the flow of electrons with our microchips and logic gates and so forth. It's beyond me. Then we can divide into groups and families. Groups or families, excuse me. We used to call them families. Now I think the proper term is groups. And they're vertical, right? So these elements are in the same group. These are in the same group. These are in the same group. Why are they in those groups? Because they have similar chemical characteristics. They behave similarly. Not exactly alike, right? Because they're different elements, but they have similar characteristics. And they're in this position because of that. Periods, on the other hand, go from left to right. Right? So these elements are not the same. But the trend is such that when you get to the end of that period, if you go one step further, like you add another proton, well, you end up with an element that looks and behaves like one in this group. So that's why it's period, right? You've heard of periodic motion. Periodic motion is where something moves, but it goes through a movement such that eventually it comes back to where it started, like a pendulum. So this period says, all right, we go over here, we get bigger and bigger and bigger and bigger, and then, we got something out here that looks more like that, so we put it over here. So we went this way, and we're back where we started. We went to back where we started. That's a period. All right. So there's the dividing line between metals and nonmetals. And when we're talking about ionic compounds, the cation, the positive charged ion, always comes from over here. And the negative ion, the anion, always comes from over here. So ionic compounds are always formed from metals with nonmetals. And covalent compounds are always formed between two nonmetals. Right? And when you fill out that chart, if you want to do the extra credit, you need to take account of these numbers of groups. Periods, the periods aren't marked here, but this is first period, second period, third period, fourth period, fifth period, sixth period, seventh period. These are all called transition metals. We have names for some of the groups. These are alkali metals. These are alkaline earth. These are halogens. These are noble gases. These are lanthanides. These are actinides. Actually, there's more to it than that. These are chalcogens, named after oxygen. These are nitrogens, named after nitrogen. That's it. Carbon group and boron group don't have names. They get left out. Another characteristic is these families, some of them, when they become charged, they only occupy one charge. They only have one charge. So the alkaline metals, these are all +1 charges. When they bond with a non-metal, they have +1 charge, that's it. Their next door neighbors have +2 charge. Now there's electronic reason for this, and we'll explain that later. How, and are we going to get to it today? Let me see. Okay, keep going. Keep going. Keep going. Oops, we already covered that chapter. Here we go. No. Oh, we are going to name compounds though. I better get a move on because I've only got 3/4 of an hour left. Let's see. We haven't even talked about safety yet. You got the safety document. Yeah, you got the safety document. There's an agreement in there. So just, you can bring that back next time we meet. Let's see. Here it is. General rules and let's see. We've got a lot of them. You keep this copy here, and when you fill these two out, this is a duplicate of that one. You keep one and give me the other. You do that when we come back. Okay. Because I know we're not going to have time to work on that one before 5 o'clock. Okay, so naming compounds. Right. We're going to start out with the simplest rules, simplest types of compounds. Binaries, where you have one element with another element, except when I give you an exception. So we'll start off binary compounds. 2 elements, and they could be ionic or covalent. Right? And we're going to have rules for each. The ionic compounds are metals with nonmetals, and the covalents are nonmetals and nonmetals. So type 1. Type 1 compounds. They're metals and nonmetals. Right? Always. The metal is always a fixed charge. It can only have one charge. So that means it can come from only the alkaline metals, the alkaline earths, or these guys right here, indium, gallium, aluminum, boron. And there are a couple in the transitions, right? Zinc is a fixed charge, cadmium is a fixed charge, and silver is a fixed charge. So any of those would be a type 1 compound. So you don't have to worry about the charge on the cation. It's always the same. The charge on the the charge on the nonmetal is also fixed, but it's based upon neutrality with the metal. If you, the noble gases have no charge, so they have to be forced to react. Typically, you can just assume that they don't react. So they have 0 charge. But as we were coming from left to right, +1, +2, +3, notice I skipped these guys. These are representative elements right here, this group, and this group. These are transition elements. So if you move from right to left, these are -1, -2, -3. When you find them in ionic compounds. Okay, that's important. When they react with metals, they have those fixed charges. All right. The metal is always just named after the element. Just name the element, that's it. So sodium would be sodium in the compound. The anion is always ended with IDE. So chlorine becomes chloride, sulfur becomes sulfide, oxygen becomes oxide, nitrogen becomes nitride, bromide or iodide, or whatever the case may be. So the important factor here is fixed metal charge. Okay, type 2s are ionic compounds between a metal and a non-metal where you have variable metal charge. So what do you do then? Well, if this is sodium chloride, for example, and we write it like this, sodium has a +1, chloride has a -1, because chloride is -1 here, sodium is +1 there, then you only need one of them. Neutrality is the target. 1 +, 1 -, that's the simplest you can get. It's neutral. For this one, the metal could have multiple charges. Right? So for instance, if we, let's pick one. From the transition metals, that's usually where they come from. Either the transition metals or right down in here, some of these metals have multiple charges. So let's pick iron. Iron can either be +2 or +3. So if we say we've got a 2+ charge on iron and we react it with oxygen, right? Oxygen has a -2 charge, 2- charge. 1 and 1 is all you need. So you have iron oxide. But when you write the name, right, how can you tell from that name how to write the compound? If this could be a +2 or +3, then you don't know. So the naming convention says you have to say what the charge is on the metal. And we do it with a Roman numeral. So it's iron 2 oxide. And that specifies the charge on iron. That's a type 2 compound. Okay. Type 3 is non-metal and non-metal. So if you react one of these non-metals with another non-metal, then you get a type 3 compound. And while these are ionic compounds, these are always covalent. But for naming purposes, we sort of borrow from the binary ionic compounds. So the second one always ends in an IDE, and the first one is just the name of the compound, the name of the element. So for instance, let's see. Well, let me keep flipping. 2. Oops. No, I want to do type 3s before we get into anything else. So type 3s are non-metal, non-metal. So what if we have, how about this one? Right. The existential threat to our existence. Carbon dioxide. For type 3 compounds, all you do is you say how many of each there are. For the first one, you never say mono. If there are 2, yeah, you say di. So you need a prefix that designates how many. And we use the Greek letter system, mono, di for 2. 1, 2, 3 is tri. Okay, those are prefixes. So this would be carbon dioxide. Tetra is 4. Penta is 5. Hexa is 6. Hepta is 7. Let's see, octa is 8. Nona is 9. And deca is 10. That's as far as we're going to go. You can go farther, but there's no need for us. So this is carbon dioxide. How about this one? Carbon monoxide. Notice we dropped one of the O's. Monooxide just didn't flow right. So we say chemists can be aesthetic too. Monoxide. So that's all you have to do. You just have to say how many there are. Let's think something more complicated. What would let's see. How about this one? Well, let me put the name up there first, and then you write it. How about silicon tetrafluoride? Silicon, right? And fluorine 4 times. So that would be the compound that relates to this name. Right? Type 3 compounds. So that's it. 1, 2s, and 3s. So if you're presented with a problem, how do you decide what to do with it? If you're given the formula and you have to name it, then you say, okay, is a metal nonmetal or a nonmetal nonmetal? If it's a metal nonmetal, it's one of these two. If it's a nonmetal nonmetal, it's one of these. Use that convention. If it's a metal nonmetal, then you have to decide, is the metal fixed charge or variable charge? So you look at your chart and say, where does it come from? Well, if it comes from here, 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 or one of these, that one, or that one, then it's type 1. Anywhere else is type 2. So those are the naming rules. Now, here's the fly in the ointment. Sometimes groups of atoms behave as single cations or anions. Those are polyatomic ions. And you got a whole list of them. Let's see, in the review document, if you look at the back, see, I'm going to draw black marks all over my paper, folks. Careful. If you look at the back, you see some useful information. Let's see, how far do we go? Right here. That's where it starts on this page. Useful information, and then you got some other stuff here. This is a list of polyatomic ions. Now, I didn't hand you out a copy of this one, but it is in the review document. These polyatomic ions are the only ones that we're going to deal with. There are many more than this. But these groups, the name of a polyatomic ion does not change. When you put it into a compound, you still call it that. Sometimes you say mono, di, tri, tetra, say how many of them there are, but you always use that name. You'll notice that all of these polyatomic ions are negatives, either 1, 2, 3 negative charges, except for one, ammonia or ammonium. Ammonium is the only positive charge in this table. The rest of them are negatives. And they follow a pattern. Some of them follow a pattern. They have what we call a homologous series. Let's see. How much more do I have to cover? And then I'll know whether I can spend time on it or not. Yeah, maybe so. Let me hold that thought until we finish the slideshow. So here are examples with polyatomic ions, right? OH is hydroxide. NO3 is nitrate. It's a -1 charge. So it takes 2 minus nitrates to balance this magnesium with a 2+ charge. Why is it a 2+ charge? Because it comes from right there. And everything in that column is 2+ charge. Okay. Well, there's the rules for 3. And here I forgot I had that slide in there. Those are your prefixes. Let's see, what else? Okay, type 3 compounds. We did carbon dioxide, sulfur hexafluoride. Or this one, 2 nitrogens and 4 oxygens, right? So you have to say, all right, where did they come from? Right, not nitrogen's right there, oxygen's right there. That means they're both nonmetals. That automatically type 3 compound. Type 3. Have you seen Shrek? Everybody seen Shrek? So what do you say? Pick 3, my lord. I thought it was right. Okay. Flow chart for naming. You can use that if you want. Let's see. That's another flow chart for naming also. All right, we'll get to acids in a second. There's a convention for naming acids. It's sort of we had to deal with grandfathered in because acids were so commonly used in alchemy. We sort of inherited names from them. So we had to sort of standardize them. And we'll talk about that in a minute. Let me show you the polyatomics. So some of those polyatomics, and you don't have to memorize them. Any information that's given to you in a review document that's useful information at the end, it will be duplicated on a paper exam. So you just need to know where it is and how to use it. If you do enough of those problems using that information, you'll automatically memorize it. Okay, before we get to acids, there are several groups in there that share common elements, and they're just in different amounts. So the easiest one to deal with is the one with chlorine and oxygen. So the polyatomic ion that has chlorine and 3 oxygens with a 1- charge is the chlorate ion. And if you take away one of these, then you have same charge, fewer oxygens. This is chlorite. You can take away one more, but we don't have any more suffixes that will fill in, so we have to add a descriptor in the front. So we use one from medical, hypochlorite. So underneath the chlorite. Then we can go one in the other direction, but we don't have a suffix for that one either. So ClO4 minus is per chlorate. Okay, so if you learn one of them and you know the progression, then you can do them all. And also, these are halogens. This chlorine is a halogen, so other halogens can be shoehorned in here also. Instead of chlorine, we could use bromine. So if you put bromine here, it'd be perbromate, bromate, bromide, heterobromide. So with one, you can get 4. There's some others like that, but they're not as extensive as this one. This one is nitrate, and this one is nitrite. Okay, these are important to know when we start naming acids too, because the relationship of these suffixes to the name of an acid is a logical progression. So I'm going to leave those up there in a while we talk about acids. Okay, when we name acids, characteristic of an acid is it always starts with a hydrogen. 1 or more hydrogens. It can have one, it can have two, three. I don't recall ever seeing 4 hydrogens in an acid. So for now, we'll just stop with 1, 2, or 3. And then you'll have some anion out here. Okay. So it could be an ion of an element, or it could be a polyatomic ion. The question in naming acids is, does this part of the molecule, the negative part, does it have oxygen in it? If it doesn't have oxygen in it, then you start the name with hydro. Okay, so if we say this, that, the first condition is no oxygen. The second condition is it dissolved in water? If it's not dissolved in water, then it's not an acid. If it's hydrogen and chlorine together like that, and it's a gas, then you name it hydrogen chloride. Just like we name any other compound. But if you put it in water, then the identifier is AQ for aqueous. So that aqueous is started with hydro because it has no oxygens. It's hydro. And then ions become X. So it's hydrochloric acid. Okay. Now, what if it has oxygen there? Say it's like this one, ClO3 instead of HCl, ClO3. So this is a 1 positive charge and this is negative charge. So it balances, right? You only got 1 hydrogen and 1 negative charge. This is 1 positive and this is 1 negative. Okay. So how do we name it then? Well, if it's got oxygen in it, you don't start with hydro. Right. The H's become X. And you say chloric acid. For this one, the ites become, let's see, chlorus. The ites become us's. So if this were an acid, it would be chlorus acid. And this one would be hypochlorous acid. And this one would be followed from that one. Instead of chloric, it would be perchloric acid. So that's what this one would be. Perchloric acid. That is a monster. Perchloric acid in concentrated form is a very effective oxidizing agent. It can take organic matter and tear it to pieces. And we used it very often in the laboratory to digest plant material and leave the mineral ash behind. It's very effective, but you have to be careful with it. If you want an explosion, take a beaker full of perchloric acid, a nice big chunk of butter, throw it in there, put it on your hot plate, turn it on the hot plate, pull the sash down, and evacuate the building because it will blow. So the way we got around that was we took our plant samples in their beakers. Of course, we had to weigh them out beforehand, and we put nitric acid in before that. Just put our nitric acid in, set it under the hood, and just close the sash and let them sit overnight. Then we can put the perchloric acid in the next morning, heat it up, it's perfectly safe. Okay, those are the rules. Oxygen, no oxygen. Simple ion or polyatomic ion. Okay, so for the simple one here, the ides become X. Okay, or for this one, the eights become X and the ites become us's. Okay, so this one is nitric acid. It's got oxygen in it, so we don't say hydro. Oh, that's a good example. What if compare this one to this one? Okay, aqueous, of course, that's required also. It has to be aqueous or it's not an acid. If it's not aqueous, then you name it like we did the previous compounds, type 1, type 2, type 3. But if it's aqueous, then you can name it as an acid, and it has to have these hydrogens, because acids are dependent upon dissociating some of these hydrogens into solution. That's where acidity comes from. The free protons in solution, well, not free actually, they bond with water. We'll talk about that later when we get to acids and bases. But how would we name this one, right? That's sulfate, right? So this one is sulfuric. H become X, acid. But this one has no oxygen, so it'd be hydro. Sulfuric acid. Okay. I know naming acids really gives students trouble sometimes if you haven't done it for a while. Okay, so there are some, let's see, flowchart naming acids. There's some naming compounds. How are we doing on time? Okay, we got time. We haven't talked about naming bases, but they're really simple. Yeah, it doesn't even talk about bases. With bases, you could have solid. Let's use an example. Sodium hydroxide is a base. Right. So if you name that, then you got a polyatomic. This is the hydroxide ion, so we just say sodium hydroxide. But if you put it in solution, you get sodium ions and hydroxide ions. This is where the base comes from. But how do we name the solution? You say aqueous sodium hydroxide. That's all there is to it. The bases are not special. Okay. Oh, that's it. Wow. Maybe I hurried too fast. Any questions?
A base can be as dangerous as an acid.
Yes, it can. In fact, the rule of thumb, when you're mixing up solutions, do as you ought to add acid to water. The reason you add acid to water and not water to concentrated acid is the heat of reaction. When you make a solution, the heat of solution of strong acids and strong bases is very exothermic, makes a lot of heat. So if you add water to acid, then the heat of reaction will vaporize that water very quickly. It's got sufficient energy to exceed the boiling point, and that means it's going to spatter and right in your face. So it's safer to take a large amount of water and add the acid to it or the base. And that way the specific heat of water will absorb that energy. Now, it'll get hot, especially if you make say a 1 molar solution. You're making a stock solution of sodium hydroxide. 1 molar is common. And then it'll get hot. So before you use it, you got to let it cool down. Especially if you're trying to make a standard solution. Right? In a volumetric flask here, there's your mark for 1 liter, say, and you put your sodium hydroxide in here, and you add water. As it dissolves, it gets hot. So what happens when something gets hot? The liquid gets hot, it expands. Right? So if you try to bring it to the mark here, then it won't be accurate because it's not at the calibrated temperature for that device, right? Which is usually 25 degrees Celsius. So you let it cool down to room temperature before you bring it up to the final volume. Okay. Well, I'm kind of curious as to how much of my discussion was missed. I won't know until I review it, process the videos. I'm still going to have to splice those two together, assuming the first one got saved. It usually does when you lose connection like that. Usually just dumps and saves what's left, and you have to start up again with a new one. Okay, so I guess we'll see you next week. If you have no questions, work those problems, and we'll review next time we meet. And I'll field your questions first.
I think I had two. So when we said acquiesce for the G, I thought the difference was whether or not it was hydro or A, like you said. And up there, we don't have an oxygen atom in the H2S. So why is that still AQ or AS? I can't quite see.
This one, hydro, that's the difference. No oxygen means hydro,
Okay, so
but oxygen, no hydro.
in the other one we had up there, it was a G rather than the AQ or AS.
Oh, I see, okay. If you have, let's see, H2S, for instance. H2S, not dissolved in water, is a gas, hydrogen sulfide. Okay, go any place, any warm spring or spring in Greenbrier County, and you'll smell hydrogen sulfide coming out of it. So while it's dissolved in water, it's an acid. Give it this name. But when it comes out of solution, when it gasifies, and you smell it, it's hydrogen sulfide.
Okay, so the difference between the G and the AS is whether or not they're soluble in water.
Yeah.
Okay.
Yeah.
And for lab, or do we actually have a lab that's specifically due next time we're in here? Like I thought on the report or on the thing, it said lab 1 was due next week. Maybe I don't know about that.
Oh, well, let's be sure I didn't make a mistake. Oh, lab 1 is your safety document,
Okay, and that was in the documents we.
your safety agreement. Yeah, that's all.
Yeah.
It's not really a lab.
Right, it's the signatures and stuff.
And then then you have introducing graphing techniques. You should have a copy of that. Just read the beginning material. You can try some of it if you want, but you're probably going to have your hands full with all this other stuff you have to do, memorize symbols and work in those problems, because there are a lot of them. Yeah. Curiosity and boredom, two best friends.
Are those problems gonna be on the test screen?
Some like them, yeah. I gave you practice doing the type of problems you'll see on test. So if you're limited in time, spend your time on those problems. But if you're a glutton for punishment, work as many as you can get wherever you can find them. Okay, we'll see you next week.